Right now, while you are lying still, something invisible is holding you together. There is a field filling this room. It reaches through the space between your hand and the screen, through the walls, through the air in your lungs, through every atom you are made of. You cannot see it or feel it. And yet, if it switched off for a single instant, every atom in your body would come apart. That field has a name. The Higgs field. You have probably met it through one picture. The field is a kind of cosmic syrup. Particles push through it. The pushing slows them down, and the slowing is mass. It is easy to remember. It is also wrong. If mass came from being dragged through syrup, anything coasting through empty space would slow and stop, and nothing does. Planets hold their orbits for billions of years. So whatever the field is doing, it is not that. And the real answer is stranger than the picture built to replace it. Pick up something near you. A phone, a cup, your own hand. It has weight. You can feel it pulling down. For most of human history, weight was simply what heavy meant, and nobody had a reason to split the idea in two. Drop a heavy rock and a light pebble at the same time, and they hit the ground together. Galileo is supposed to have shown this, and whether or not he climbed a tower to do it, the result is real, and you can check it yourself with 2 stones in your hand. The heavy rock is pulled harder by gravity. Much harder. So why does the harder pull not win the race? The answer is that the heavy rock is also harder to move. The same property that makes gravity grab it more strongly also makes it more stubborn against being sped up. The two effects scale together so exactly that they cancel, and everything falls at the same rate. That exact cancellation bothered physicists for 3 centuries, and it is the seed of Einstein's entire theory of gravity. But set that aside for now, and notice what it tells us. There are 2 things hiding inside the word mass. One is how hard gravity pulls on you. The other is how hard it is to get you moving, or to stop you once you are moving. Push a stalled car on a flat road, far from any hill, where gravity is doing nothing to help or resist. The car still fights you. It does not want to start moving. That resistance, that stubbornness against a change in motion, has a name: inertia. And it is the deeper of the 2 ideas, because it shows up even when gravity is taken completely out of the picture. When a physicist says the Higgs gives particles mass, this is the mass they mean. Not weight. Inertia. The stubbornness. The thing that makes a particle resist being shoved. Hold on to that, because it dissolves the syrup picture in one move. Syrup gives you drag, and drag depends on speed. The faster you push through syrup, the harder it pushes back, and the moment you stop pushing, syrup brings you to rest. Inertia is the opposite. A thing with inertia, once moving, keeps moving forever with no field pushing back at all. It only resists changes. Steady motion costs nothing. So whatever the Higgs is doing, it cannot be drag, because drag and inertia behave like opposites. A field that produced drag would violate the most basic law of motion we have. A field that produces inertia is allowed. We need a field that does not slow steady motion at all, but does make particles resist being sped up or slowed down or turned. A field that is invisible to a particle coasting in a straight line, and only makes itself felt the instant that particle tries to change what it is doing. It sounds like asking for a contradiction. You want something that fills all of space, that touches every particle, and that a particle moving through it cannot feel at all unless it accelerates. Nature, it turns out, can do exactly this. And the reason it can is the reason we had to throw out the idea of particles as little balls and replace them with something stranger. Everything is a field first and a particle second. Even you. What does it mean to say that? That is the next thing we have to take apart, because until the word field stops being a vague cloud in your mind and becomes something specific, the Higgs will never make sense. What is a field, really, when the thing it is made of is not water and not air and not anything you can hold? Start with something you can actually feel. A magnet. Bring two magnets close and you feel a push or a pull across a gap where there is nothing. No string. No rod. Empty air, and yet force crosses it. For a long time that was disturbing. Action at a distance, force reaching across nothing, looked like magic, and serious people refused to accept it. The fix was the idea of a field. The magnet does not reach across the gap. Instead, the magnet fills the space around it with a condition, an invisible state of readiness, and the second magnet responds to the condition right where it sits. The field is the middleman. It is the space itself being put into a state. Iron filings on paper over a magnet make the state visible. They line up along the lines of the field. The field was always there. The filings just let you see it. Now make the leap that took physics most of the 20th century to fully commit to. That field, the magnetic field, is not a description of empty space reacting to a magnet. It is a real, physical thing, with energy in it, able to carry waves, able to exist on its own with no magnet anywhere in sight. You already know one of those waves. Light is a ripple in the electric and magnetic field, traveling on its own, long after whatever made it has gone. The light reaching your eyes from across a room is the electromagnetic field vibrating. There is no little particle of light that is separate from the field. The particle, the photon, is what one ripple of that field looks like when you measure it. The field is the thing. The particle is the field doing something. In the deepest version of physics we have, the universe is not made of particles moving through space. It is made of fields filling space. Several of them, overlapping, occupying the same room at the same time, each one a different kind of substance spread through everything. There is an electron field. Not electrons moving through space, an electron field filling space. And what you call an electron is a single tight knot of energy in that field, a place where the field is excited. Pluck the electron field in one spot and a knot appears, and we name the knot an electron. Let the field go quiet, and the electron is gone, absorbed back into the smooth nothing it came from. There is a field for every kind of fundamental particle. A field for the up quarks and the down quarks that build the cores of atoms. A field for the photon. A field for the particles that carry the weak nuclear force. Each one fills all of space. Each one can be plucked. Each pluck is a particle. When two particles collide and turn into different particles, what is really happening is that energy is being passed from one field to another, one field going quiet while another rings. So before the Higgs ever enters the story, the picture is already this. Empty space is not empty. It is layered with fields, all silent and smooth, when nothing is happening, all capable of carrying ripples we call particles. The vacuum is full. It was always full. It is the most substantial nothing imaginable. And the trouble starts right here. The trouble the Higgs was born to fix. When you write down the equations for these fields, the most natural and most beautiful equations, the kind that physicists trust because their symmetry is so clean, those equations insist on something brutal. Every ripple must travel at the speed of light. Every particle must be massless. All of them. The electron, the quarks, the carriers of the weak force, every single one comes out of the math weighing exactly nothing, racing at light speed, unable ever to slow down or stop or hold still long enough to clump into an atom. A universe like that has no chemistry. No atoms. No stars. No you. It is light all the way down, forever scattering, never settling. Yet here you are, made of particles that very clearly do have mass, that very clearly can sit still. So either the beautiful equations are wrong, or something is hiding in them that we have not accounted for. Something that breaks the rule that everything must be massless, without destroying the symmetry that made the equations beautiful in the first place. That is the knot. The math demands massless particles. Reality is full of massive ones. For about a decade in the middle of the 20th century, that contradiction sat at the center of physics like a stone nobody could move. The question that cracked it did not come from particle physics at all. It came from a completely different room, from people studying metals so cold that electricity flowed through them with no resistance at all. People studying superconductors. And the thing they noticed in those frozen metals was a clue to the deepest structure of empty space. What does a cold lump of metal know about the vacuum of the universe? That connection is the strangest turn in this whole story. Take a wire and cool it down. Not cold like a winter night. Cold like a few degrees above the lowest temperature that can exist, the temperature where atoms almost stop trembling entirely. In certain metals, when you reach that cold, something abrupt happens. The electrical resistance does not just drop. It vanishes. It becomes exactly zero. Start a current flowing in a loop of that metal, and it will flow around and around for years with nothing to keep it going, losing nothing, like a wheel that spins forever because there is no friction anywhere to slow it. That is superconductivity, and when it was first discovered, it made no sense at all. Electrons pushing through a normal metal are constantly bumping into things, scattering off the jiggling atoms, losing energy as heat. That bumping is electrical resistance. It is why wires get warm and why your phone heats up. For the bumping to stop completely, the electrons would have to somehow stop behaving like a crowd of individuals, each making its own way through traffic, and start behaving like one single coordinated thing that the traffic cannot grab. Which is exactly what they do. Below that critical cold, the electrons pair up, and the pairs lock into a single shared state, a vast coordinated condensate that fills the whole metal and moves as one. You cannot scatter one electron out of it without fighting the entire condensate, and the condensate is too big to budge, so nothing scatters, and the resistance is gone. The electrons stop being a mob and become an ocean. Inside a superconductor, magnetic fields get expelled. Push a magnet toward a superconductor and the field cannot get in. It dies away within a thin skin at the surface and goes no deeper. A magnetic field, which in open air reaches out across a room with no trouble, suddenly cannot penetrate more than a hair's width into this cold metal. The field's reach has been cut short. It has become in effect short-ranged. and there is a precise way physicists describe a force whose reach has been cut short. They say its carrier has gained mass. Hold on to that wording, because it is the whole key, a force that reaches across infinity, like magnetism in open air or like light, is carried by a massless particle. A force that dies off after a short distance is carried by a massive one. The heavier the carrier, the shorter the reach. Inside the superconductor, the photon, the carrier of the electromagnetic field, the particle that is supposed to be massless and reach forever, starts behaving as though it has weight. It cannot get far. The condensate of paired electrons has reached into the equations of light and given the photon an effective mass that it does not have anywhere else. The photon did not change. The space it was traveling through changed. The metal is filled with a condensate, a substance with a single coordinated value spread all through it, and a photon moving through that substance drags against it in a way that mathematically looks exactly like mass. Not drag in the syrup sense, remember. Not a slowing of steady motion. The equations specifically produce the short reach, the inability to spread far, which is the signature of mass, while leaving the deeper rules intact. A physicist named Philip Anderson looked hard at this in the early 1960s. He understood that inside a superconductor the photon effectively gains mass because the vacuum of the metal is not empty, it is filled with the condensate. And he made the leap that most people did not. He suggested that the same trick might explain the massive particles in the rest of physics. What if the vacuum of the entire universe, the so-called empty space everywhere, is also filled with some kind of condensate? Not a metal, not electron. Something more fundamental, present everywhere, even in the deepest void between galaxies. And what if the particles that look massive to us look that way for the very same reason the photon looks massive inside the cold wire? Because they are all moving through a filled vacuum, and the filling reaches into their equations and gives them the short reach we read as mass. This is the idea that one physicist, years later, described as the most surreal thing he had ever learned. That we are, all of us, living inside something very much like a superconductor. That the emptiness around you is closer to the frozen condensate inside that wire than it is to true nothing. He said when he tried to tell people this at dinner, they looked at him like he had lost it. We are living in a superconductor, basically. And he could prove it, if only they would give him 5 hours and let him show the equations. The reason it sounds insane is that the condensate filling our universe is not made of paired electrons, and it is not cold, and it is not sitting in a wire. It is its own thing, a field that has no business being there by the clean logic of the original equations, switched on everywhere, with the same non-zero value in this room and on the far side of the observable universe. A field that, like the superconductor's condensate, reaches into the equations of other particles and hands them mass. That field is the Higgs field. And the version of the story where it gives mass to particles by being a syrup they push through has it almost backward. It does not slow them as they move. It changes the rules of the space they move in, the way the cold condensate changes the rules for light inside the wire. The particles are not wading through it. They are living inside it, the way a fish does not push through water so much as live in a world where water is simply how things are. But naming the field is not the same as understanding why it has to be there. Anderson had the analogy. What he did not have, what nobody had yet, was the precise reason the universe was forced to switch this field on in the first place. Because a field that fills all of space, with energy in it everywhere, is not a small thing to add to your theory. You do not get to just sprinkle a condensate across the cosmos because it would be convenient. Something has to make it unavoidable. What made it unavoidable was a contradiction in the one force we have not talked about yet: the weak nuclear force. The force responsible for one specific kind of radioactivity, for the first step that lets the sun burn, for turning one kind of particle into another deep inside every star. The weak force was breaking the math, and the only known repair was to fill the universe with a field. Why would a force buried inside radioactive decay have anything to do with the structure of empty space? That is the contradiction we have to walk into now. The weak nuclear force is the quiet one. Gravity holds you to the floor. Electromagnetism runs every chemical reaction in your body and every screen and wire around you. The strong force, which we will get to, glues the cores of atoms together. The weak force does something less obvious and more profound. It changes particles into other particles. It lets a down quark become an up quark. It lets one element transmute into another. Without it, the sun could not begin the chain of reactions that makes it shine, because the very first step of fusing hydrogen requires a proton to turn into a neutron, and only the weak force can do that. So the weak force is real, it is essential, and it has a strange property that turned into a crisis. It is short-ranged. Extremely short-ranged. Electromagnetism reaches across a room and across the galaxy. The weak force reaches less than the width of a single proton before it dies away to nothing. By the logic we built in the last act, that short reach means its carriers are heavy. Very heavy. The particles that carry the weak force, called the W and the Z, weigh as much as a medium-sized atom, roughly 85 to 95 times the mass of a proton, all packed into a single fundamental particle. They are some of the heaviest things of their kind we have ever found. Now the trap closes. The equations that describe forces, the ones physicists trusted most, work because of a deep symmetry. The symmetry is what keeps the math consistent, what prevents it from spitting out nonsense like infinite probabilities. And that same symmetry has an iron requirement built into it. The carrier of a force described this way must be massless. It must reach across infinity. The symmetry that makes the equations work forbids the carrier from having any mass at all. Read those two facts together, and you have the contradiction that stopped physics cold. The symmetry says the weak force carriers must be massless. The experiments say they are enormously heavy. Both cannot be true. Either the beautiful symmetric equations are simply wrong for the weak force, in which case physics loses its most powerful tool, or there is some way for the carriers to be heavy, while the equations still secretly keep their symmetry. Throwing out the symmetry was not really an option, because without it the math gives infinite, meaningless answers. The equations only stay sane while the symmetry is intact. So the carriers had to be massless according to the rules that keep the theory alive, and yet massive according to every measurement. For years there was no way through. The escape is subtle, and it is the whole intellectual heart of the Higgs. The trick is to let the equations keep their perfect symmetry, while the world those equations describe settles into a state that hides it. The laws stay symmetric. The situation does not. The symmetry is still there in the rulebook, fully intact, which keeps the math healthy, but the universe has rolled into a particular configuration that does not show the symmetry on its surface. There is a homely picture for this, and unlike the syrup, it actually points at the right mechanism, so hold it lightly, and then we return to the physics. Imagine a pencil balanced perfectly on its tip. While it stands there, it is completely symmetric. There is no special direction. Every way it might fall is equally likely, and the whole setup looks the same from any side. But that balance cannot last. The pencil falls, and the instant it falls, it points one specific way. The symmetry of the laws is untouched. Every direction was equally available, but the actual pencil now picks out a direction, and the world it creates is no longer symmetric. The symmetry was hidden, not destroyed, by the system settling into one of many equal possibilities. The universe did the same thing with a field. In the first unimaginably hot instant after the Big Bang, the Higgs field had a value of 0 everywhere, balanced like the standing pencil, perfectly symmetric, and all the particles were massless, and the weak force reached as far as light. Then the universe cooled. And as it cooled past a certain point, that balanced 0 became unstable, the way the upright pencil is unstable. The field could lower its energy by falling away from 0, by switching on, by taking a non-zero value everywhere. So it fell. Everywhere at once, the Higgs field rolled off its perch and settled into a non-zero value that has filled all of space ever since. That switched-on field is the condensate. That is the moment our universe became, in the language of the cold wire, a kind of superconductor. Before the fall, massless particles and a long-range weak force. After the fall, the field is on everywhere, and it reaches into the equations of the weak force carriers exactly the way the condensate reached into the photon inside the cold metal, and it hands the W and the Z their enormous mass, cutting the weak force down to its tiny reach. The symmetry in the rulebook never broke. The universe just rolled into a state that hides it, and in that hidden state, mass appears. This is why the field had to exist. Not to give you weight. To save the weak force from a contradiction that would have made it mathematically impossible. The giving of mass to the W and Z was the entire point. Everything else the field does, including the small contribution it makes to the electron and the quarks, came along as part of the same fall. And this is the answer to a suspicion many people have when they first encounter the Higgs. At first glance, it can feel like a patch, a clever addition designed to rescue a theory that was beginning to break apart. In one sense, that is true. The Higgs mechanism was introduced to solve a serious problem buried inside the equations of particle physics. But it was not an arbitrary fix. The same underlying idea had already appeared in nature, inside superconductors. Physicists were not inventing a loophole. They were recognizing a pattern the universe had already revealed. Then something remarkable happened. In 1964, several physicists working independently arrived at essentially the same solution within a matter of months. None of them knew exactly what the others were doing. They were following the mathematics, and the mathematics kept leading them to the same place. But one of them took the idea a step further. A field is already a bold prediction. A field that fills all of space is bolder still. Yet one physicist realized that if the field was real, it could not come alone. It should have a particle associated with it, a particle nobody had ever seen. Making that prediction was easy. Proving it would take almost 50 years. So who were the people who uncovered this idea, and why did one of them become forever linked to a particle that remained invisible for half a century? In 1964, within the span of a few months, 3 small groups of physicists arrived at the same escape route without talking to each other. In Belgium, Robert Broud and François Englert. In Scotland, working alone, Peter Higgs. And in London, Gerald Guralnik, Carl Hagen, and Tom Kibble. 6 people, 3 papers, 1 idea, all in a single year. The history books would spend decades arguing over whose name should go on it, and the honest answer is that it belonged to all of them. Their papers were short. They were not splashy. They described, in the dense private language of the field, how a force carrier could acquire mass without breaking the symmetry that the math depended on. How you could let the field fall, hide the symmetry, and watch the carriers get heavy. It was a quiet solution to a technical crisis, the kind of thing that might have stayed buried in journals forever, read by a few hundred specialists. What lifted Peter Higgs slightly apart from the others was one extra sentence. He noticed something the rest had not spelled out. If empty space is filled with this field, and the field has fallen into a non-zero value everywhere, then the field is not perfectly rigid. It can wobble. You can push on it. And a wobble in a field, by everything we said earlier, is a particle. So the filled vacuum should not be silent. It should be possible, if you hit it hard enough, to make the field itself ring, to knock a ripple loose, and that ripple would show up in an experiment as a brand new particle that had never been seen. This is the boson. The Higgs boson is not the field, it is the field twitching. It is the smallest possible vibration of the substance that fills all of space, the way a single photon is the smallest vibration of the electromagnetic field. The field is everywhere and silent and gives mass. The boson is the rare, fleeting moment when you manage to slap that field hard enough to make it quiver, and the quiver is a particle you can detect. It was a daring thing to put in writing, because it turned a clever piece of mathematics into a bet. If the field is real, then the particle is real, and the particle can in principle be found. If you look hard enough and the particle is not there, the whole idea is dead. Higgs had handed the experimenters a target. He just could not tell them how heavy it would be, which meant he could not tell them how hard they would have to hit the vacuum to shake it loose. That number, the mass of the boson, was the one thing the theory could not predict. It might be light enough to find soon. It might be so heavy that no machine humans could build would ever reach it. Nobody knew. They would have to search blind. And then they waited. Not a year. Not 10 years. Almost half a century. Peter Higgs published that paper as a young man and spent most of his life not knowing whether the particle he had predicted existed. He grew old waiting. Some of the others died before the answer came. Robert Broud died in 2011, 1 year before the discovery, never knowing. That is a long time to live with a question you cannot answer. A long time to wonder whether the most important thing you ever wrote was true or was a beautiful mistake. The nickname did not help. At some point, the Higgs boson got tagged with the phrase, the God particle, and it stuck to everything, every headline, every documentary, and physicists have hated it ever since. The name did not come from any religious idea about the particle. It came from a book. A physicist named Leon Lederman wanted to write a popular book about it and wanted to call it the goddamn particle, a joke about how maddening it was to find, how it kept refusing to show up. His publisher would not allow the word. They cut it down to the God particle, the marketing stuck, and a piece of frustrated humor became a grand cosmic label that misleads people to this day. Peter Higgs himself disliked it. The particle has nothing to do with God. It has to do with a field, and a contradiction, and a frozen wire, and a pencil falling off its tip. So by the late 1960s, the theory was complete enough to make a clear demand. Somewhere out there was a particle, a ripple in the universal field, with an unknown mass, and either we would find it and confirm that empty space is full, or we would fail to find it and have to admit we had been wrong about the deepest structure of the vacuum. The theory could not be half true. The field is on, or it is off. The particle exists, or the idea is wrong. Confirming it would require building the most complicated machine the human species has ever attempted. A ring of magnets 17 miles around, buried under the border between two countries, cooled colder than deep space, smashing protons together at very nearly the speed of light, billions of times a second, to recreate for a fraction of a second the heat of the universe just after it began. Only in that heat could the vacuum be slapped hard enough to shake one ripple loose. And even then, the ripple would last so briefly and disappear into other particles so fast that no detector could ever see it directly. They would have to catch its echo. They would have to prove the existence of something by finding the specific debris it leaves behind as it dies. Before we go inside that machine, there is a myth we have to clear away first, because almost everyone carries it, and it makes the discovery seem to mean more than it does. The myth is that the Higgs gives mass to everything, that it is the source of all the weight in the world, that without it, nothing would be heavy. The truth is stranger and humbler. The Higgs is responsible for almost none of the weight you would read on a bathroom scale. Your mass, the mass of your body, the mass of nearly everything you can touch, comes from somewhere else entirely, somewhere the Higgs barely reaches. If the Higgs is not where your weight comes from, then where is it coming from? Of all the mass in your body, the Higgs field is directly responsible for only about 1% of it, maybe a little less. The other 99% comes from a completely different source, one that has nothing to do with any field switching on everywhere, and understanding where it comes from is the part that reorganizes how you think about what you are made of. Walk down into your own body. You are made of cells, the cells of molecules, the molecules of atoms. Each atom is a dense little core, the nucleus, with a cloud of electrons around it. Almost all of your weight is in those cores, because the electrons are nearly weightless by comparison. So your mass is, to very good approximation, the mass of all the nuclei in your body. And each nucleus is built from protons and neutrons. So the real question is simple. Where does the mass of a proton come from? A proton is made of 3 smaller particles called quarks, 2 up quarks and 1 down quark, held together by the strong nuclear force. Now you would expect, reasonably, that if you add up the masses of the 3 quarks inside a proton, you would get the mass of the proton. That is how it works for ordinary objects. The mass of a chair is the mass of its parts. But the quarks do not add up. The 3 quarks inside a proton, taken on their own, account for only about 1% of the proton's mass. You could weigh all 3 quarks, add them carefully, and you would be missing 99% of the answer. The proton weighs far, far more than the things it is made of. The missing mass is not made of anything. It is energy. It is the energy of the strong force itself, the violent, restless field that binds the quarks together, churning inside the proton at a fury that never stops. The quarks inside a proton are never still. They are flying around near the speed of light, bound by a force so strong it will not let them escape, and the field gluing them together is packed with energy. And energy, by the most famous equation in all of science, is mass. Einstein's relation does not only say you can turn mass into energy in a bomb or a star. It says the reverse, all the time, quietly. Energy has weight. A box of light weighs more than an empty box. And a proton, which is mostly the boiling energy of the strong force trapped in a tiny volume, weighs almost entirely because of that trapped energy. So your weight is, overwhelmingly, bound energy. The stubbornness of the strong force, frozen into mass by Einstein's equation. When you step on a scale, almost everything that number measures is the energy of the fields inside your protons and neutrons, raging away in a space smaller than you can picture, held in by a force that refuses to let go. You are not heavy because of the Higgs. You are heavy because of the energy it takes to hold your quarks together. Where does the Higgs come in at all, then? It comes in for that last 1%, and for something more important than weight. The quarks themselves, the up and the down, do have a small intrinsic mass of their own, and that small mass, the intrinsic mass of the individual quark before you bind it to anything, that is the Higgs. The electron's mass is the Higgs too, fully, because the electron is not bound up by the strong force. It stands alone, and its entire small mass comes from the field. So the Higgs is not nothing. It sets the mass of the fundamental particles, the truly elementary ones that are not made of anything smaller. It just turns out that those fundamental masses are tiny, and most of what you weigh is the energy of binding them together. But do not let the small number fool you into thinking the Higgs barely matters. That 1% is load-bearing in a way the other 99 could never be. The reason is the electron. The mass the Higgs gives it is what sets the size of every atom. An electron's mass determines how tightly it can be held to a nucleus, which sets the size of the electron cloud, which is the size of the atom, which is the size of everything. Make the electron's mass even a little different, and chemistry changes, bonds change, the spacing of every molecule changes. And the tiny masses the Higgs gives the up and down quarks are what make the neutron just slightly heavier than the proton, by about 0.1%. That tiny difference is why neutrons can decay into protons, and why the early universe ended up with the exact mix of hydrogen it needed to make stars and water and you. Tilt the Higgs values slightly, and that balance breaks, and you get a universe of only hydrogen, or no hydrogen at all, either of which is dead. So the Higgs does not make you heavy. It does something more delicate. It tunes the masses of the fundamental particles to the precise values that let atoms exist. Let chemistry happen. Let the neutron be heavier than the proton by just the right sliver. It is responsible for the structure of matter, not the weight of it. The weight is the strong force. The structure is the Higgs. And a universe needs both, or it is light and dead, or it is heavy and dead, and there is no you in either one. The discovery everyone celebrated in 2012, the God particle, the field that gives mass to the universe, gives almost none of the mass you actually have. It does something subtler and arguably more important. It makes matter possible at all. Which means the question of whether that field is really there, whether the boson really exists, was never just a technical footnote. It was a question about whether our entire picture of why atoms can exist was right or wrong. And to answer it, they had to build the machine and slap the vacuum and wait for it to ring. What does it actually take to shake one ripple loose from the field that fills the universe? To shake a ripple out of the Higgs field, you have to concentrate an enormous amount of energy into a space smaller than an atom. The field is stiff. It does not wobble easily. The boson it produces is heavy, about 133 times the mass of a proton, and by Einstein's equation, making something that heavy out of energy requires a colossal amount of energy poured into a single point. The only way we know to do that is to take two particles and crash them together so hard that, for an instant, the collision point holds the kind of energy that filled the universe a tiny fraction of a second after it began. That is what the Large Hadron Collider is for. It is a ring 17 miles around, sunk 100 meters underground beneath the border of France and Switzerland, lined with thousands of magnets chilled to colder than the empty space between stars, colder than almost anywhere in the natural universe. Inside two thin pipes, beams of protons are whipped around the ring by those magnets, accelerated until they are moving at all but a sliver below the speed of light, going around the 17-mile loop more than 11,000 times every second. Then, at 4 points around the ring, the two beams are steered into each other, and the protons collide head-on. Most of the protons miss. They are unimaginably small, and the beams are mostly empty space, so the machine fires bunches of hundreds of billions of protons at a time, crossing through each other 40 million times a second, to make sure that somewhere in each crossing a few protons score a direct hit. When two do collide squarely, their energy is dumped into a volume far smaller than a proton, and out of that flash of pure energy, new particles condense into being. Heavy ones. Particles too massive to exist in the calm of ordinary space, brought into the world for an instant by borrowing the energy of the crash. Once in a great while, about once in every billion or so collisions, that energy shakes the Higgs field hard enough to knock one ripple loose, and a Higgs boson flickers into existence. And then, almost instantly, it is gone. The boson is desperately unstable. It exists for less than a billionth of a trillionth of a second before it falls apart, decaying into other, lighter particles. There is no hope of ever seeing the boson itself. By the time any detector could register anything, the boson is long dead. You will never photograph it. You will never trap it. The only thing you can ever catch is the wreckage. This is the part that makes the achievement almost unreasonable. The Higgs boson is detected the way you might prove a ghost walked through a room by finding the exact pattern of dust it disturbed. When the boson dies, it decays into specific combinations of other particles, sometimes a pair of photons, sometimes a spray of heavier particles that themselves decay further, and each of those combinations carries a precise total energy that adds back up to the mass of the boson that made them. So the detectors, vast cathedrals of sensors wrapped in perfect layers around the collision point, catch the spray of debris from billions upon billions of collisions, measure the energy and path of every fragment, and look for the faint statistical fingerprint of a parent particle of one specific mass decaying again and again. The trouble is that almost everything else in those collisions also produces sprays of debris that can fake the signal. Most of the photon pairs and particle showers come from ordinary, already understood physics, not from a Higgs at all. The boson signature is a tiny excess, a small bump in the data at one particular mass, hiding inside a roaring background of look-alike events. Finding it is like listening for a single specific voice in a stadium of 100,000 people all shouting, and being sure, statistically, beyond any reasonable doubt, that the voice is really there and is not your imagination stitching a pattern out of noise. To be sure, physicists hold themselves to a brutal standard. They do not announce a discovery when the bump merely looks real. They wait until the odds of it being a random fluke fall to less than about 1 in 3.5 million. They demand that level of certainty because the history of physics is littered with bumps that looked real and melted away with more data, and nobody wanted to announce the find of the century and be wrong. On the 4th of July, 2012, in a packed auditorium at the laboratory, two separate teams who had been searching independently, each not allowed to see the other's results until the end, so that neither could nudge the other toward a wished-for answer, stood up and presented the same bump at the same mass, about 133 times the mass of a proton. Both teams, working blind to each other, found a new particle at the same place, with the certainty the standard demanded. A 50-year wait ended in a single morning. Peter Higgs, by then in his 80s, was in the audience. He wiped his eyes. He had published the prediction as a young man and lived long enough just to watch a room full of people confirm that the field he imagined was real, that empty space really is full, that the vacuum really does ring when you hit it hard enough. The following year, he and François Englert were given the Nobel Prize. Robert Brout, who shared the original insight, had died 2 years too early to be eligible, since the prize is not given after death. Peter Higgs lived another decade and died in 2024, at 94, having spent almost his entire adult life first, not knowing if he was right, and then, for his last 12 years, knowing that he was. It is tempting to end the story there, on the triumph, the confirmation, the old man's tears. Most tellings do. But that ending hides the part that actually keeps physicists awake, because the discovery did not close the book. It opened a worse problem. The boson they found weighs a very specific amount, and that specific amount should, by everything else we understand, be impossible. The number is wrong. Not wrong as in our measurement is off. Wrong as in the theory cannot explain why it is so small, and the more carefully you look, the more it seems like the universe is balanced on a knife edge for no reason we can find. Why should the most important particle we ever discovered have a mass that our best physics says it should not be able to have? That is the crack in the triumph, and we have to look straight at it. The Higgs boson weighs about 133 proton masses. That sounds like a fine, ordinary number, nothing alarming about it. The alarm only appears when you ask the theory to predict it from scratch, and the theory comes back with an answer that is wrong by a factor so large it does not fit in a sentence. The trouble is the vacuum itself. The Higgs field fills all of space, and because it fills all of space, it is constantly interacting with every other field that also fills all of space. The vacuum is not quiet. It boils with what physicists call quantum fluctuations, brief flickers where particles of every kind pop into being and vanish again, borrowing energy for an instant and paying it back. These flickers are not imaginary. We measure their effects. And every one of those flickering fields tugs on the Higgs, and every tug should add to the Higgs boson's mass. When you add them all up, the contributions from the heaviest things the Higgs talks to, the corrections should drive the Higgs mass up to something astronomically huge, near the highest energy scale in physics, a number, something like 10 million billion times larger than the mass we actually measure. The math wants the Higgs to be enormous, catastrophically enormous. And instead it sits at about 133 proton masses, gentle and small, as if all those gigantic tugs had somehow canceled each other out to leave a tiny remainder. For them to cancel that precisely is like adding a list of huge positive and negative numbers, each in the trillions, and having them sum to almost exactly 0, leaving you with a 5. Nothing in the theory requires that cancellation. It just has to happen. To the accuracy of dozens of decimal places, or atoms could not exist. The Higgs mass appears to be balanced on a needle, fine-tuned to a degree that looks absurd, with no known reason for the balance to hold. Physicists have a name for the discomfort this causes. They call it the naturalness problem, or the hierarchy problem, and it has been the central unsolved worry in particle physics for 40 years. A theory feels natural when its numbers come out roughly the size you would guess, without delicate cancellations. The Higgs mass is the least natural number we know. It is as though you walked into a room and found a pencil balanced on its tip, perfectly still, and were told it had been standing there for 14 billion years. You would not think you had gotten lucky. You would think something was holding it up that you could not see. For a long time, the favorite candidate for the invisible hand was an idea called supersymmetry, a proposed doubling of all the particles, where every particle we know has a heavier partner we have not yet found. If those partners existed, their tugs on the Higgs would automatically cancel the dangerous ones, and the small Higgs mass would stop being a miracle and become a guarantee. It was a beautiful idea. It was elegant enough that many physicists were sure the collider would find those partner particles right alongside the Higgs. It did not. The machine that found the Higgs has now run for years at higher and higher energies, and the partner particles have not appeared. Not at the masses the elegant version predicted. The simplest, most natural form of supersymmetry, the one that would have neatly solved the balancing problem, is largely ruled out by the absence of any sign of it. So the most loved solution to why the Higgs is so light has gone quiet, and nothing has clearly taken its place. We found the particle. We confirmed the field. And in doing so, we exposed a hole in our understanding that we cannot yet fill. The Higgs mass should not be what it is. The cancellation that keeps it small should not happen on its own. Either there is new physics we have not found that protects it, hiding just out of reach of our machines, or the number really is just a fantastically improbable accident, or the cancellation is enforced by something we have not even imagined. There is one more possibility, and it is the one that makes some physicists uneasy enough to avoid saying it out loud. Maybe the Higgs mass is what it is because if it were anything else, there would be no one here to measure it. In a universe where the cancellation came out differently, atoms would not form, chemistry would not happen, and no observer would ever exist to ask why the number was strange. So perhaps the number is small not because a mechanism makes it small, but because only the universes where it happens to be small ever contain anyone to notice. That kind of reasoning sits at the very edge of what counts as physics, because it can explain anything and predict nothing, and a lot of people working on this would rather find a real mechanism than accept that the answer is, we are here, so it must be. What stays with me about all this is the shape of it. We chased one question for 50 years, built the largest machine in history, found exactly what we were looking for, and the prize for success was a deeper and harder question than the one we started with. The Higgs did not finish physics. It pointed at a gap underneath the floor we thought we were standing on. And the gap goes deeper than the question of why the mass is small. Because once you accept that the Higgs field is sitting in a valley, in a particular value it rolled into when the universe cooled, you are allowed to ask a darker question. Is this valley the bottom? Or is the field resting in a dip partway down a slope with a deeper valley somewhere below it, one it has not found yet? If the Higgs field could roll again, what would happen to everything built on top of it? That question has a name, and physicists have actually run the numbers, and the numbers are not entirely comforting. Think back to the pencil falling, and to the field rolling off its perch as the universe cooled. The field did not fall to nowhere. It rolled into a valley, a low point in its energy, and it has been sitting at the bottom of that valley ever since, holding the same value everywhere, giving mass to everything, keeping atoms possible. The whole stability of the world we live in rests on the assumption that the valley the Higgs field is sitting in is the true lowest point. The actual bottom. The place where it will stay forever because there is nowhere lower to go. But there is no law that guarantees this. When physicists take the measured mass of the Higgs boson and the measured mass of the heaviest known particle, the top quark, and feed those two numbers into the equations that describe the shape of the Higgs field's energy landscape, they can map out the valley. They can ask whether the dip the field is resting in is the deepest one, or whether the landscape keeps going down somewhere far away into a deeper valley the field has not reached. With the numbers we have measured, our valley does not appear to be the deepest one. It appears to be a dip on a slope, a ledge, with the ground continuing downward somewhere far out in the field's range. In the language of the field, the vacuum we live in is not stable. It is what they call metastable. It is a ball resting in a small hollow near the top of a hill, stable enough to sit still for an enormous time, but not truly at the bottom, with a deeper drop waiting beyond a barrier it would have to cross. What keeps the field in its hollow is that barrier, a ridge of higher energy it would have to climb over before it could roll down to the deeper valley. Classically, it can never get over. It does not have the energy. But the vacuum, as we have seen, is not classical, it flickers. And quantum fields can do something forbidden in everyday physics. They can tunnel, passing through a barrier they could never climb, appearing on the far side without ever having gone over the top. It is rare, almost unimaginably rare, but the probability is not zero. Somewhere, sometime, in some tiny patch of space, the Higgs field could tunnel through the barrier and discover the deeper valley. If that happened, the consequences would not stay local. The patch where the field found the lower value would have lower energy than everything around it, and that lower value would be contagious. A bubble would form, a region where the Higgs field sits at its new, deeper value, and inside that bubble, the laws of physics would be different. The masses of particles would be different. Atoms as we know them would not hold together. And the bubble wall, the boundary between the old vacuum and the new, would expand outward at nearly the speed of light, converting everything it touched into the new state, silent and unstoppable, swallowing stars and galaxies as it grew, with no warning possible because nothing travels faster than the wall that would carry the news. If our vacuum is metastable, and the measurements suggest it might be, the expected time for it to tunnel is vastly longer than the current age of the universe. Not a little longer. Longer by a number of zeros that makes the age of the universe look like an eye blink. The universe is about 14 billion years old. The estimated lifetime of the vacuum, if it is metastable, runs to a figure with so many more years that there is no way to feel the difference. Long before any such bubble could be expected to form by chance, the stars will have burned out, the galaxies will have drifted apart, and the universe will have grown cold and dark and empty on its own, through ordinary aging, many times over. The vacuum decay is not a thing that is coming for you, or your descendants, or any structure that will ever exist. It is a statement about the deep mathematical shape of the field, not a forecast. So why does it matter if it will never happen on any timescale that touches anything real? It matters because of what it tells us about the field. The fact that the Higgs field may be sitting in a hollow rather than at the true bottom is another clue that we do not understand it fully. A truly stable vacuum, a field resting at the true lowest point, would be a tidy, finished thing. A metastable one is a field caught partway, resting on a ledge, its final state still undecided in the far future. And whether it is stable or metastable depends on a knife edge, on the exact masses of the Higgs and the top quark, the very numbers we just said the theory cannot explain. We are sitting almost exactly on the boundary between a stable universe and a metastable one, and nobody knows why we are perched right there, at the edge, rather than safely inside one or the other. The Higgs keeps landing on edges. The mass of the boson sits on the edge of impossibly fine-tuned. The vacuum sits on the edge between stable and not. The neutron sits on the edge of being just heavy enough to decay. Every time we measure something about the Higgs precisely, it turns out to be balanced at a boundary, as if the universe had been set up right at the dividing line in every direction at once. That might mean nothing. It might be coincidence stacked on coincidence. Or it might be the largest unsolved hint in physics, a pattern pointing at something underneath that we have not learned how to see. And there is one more thing the Higgs might be doing that we have barely touched, a job it might be performing in secret. Because the field that gives mass to ordinary matter might also be the one doorway connecting our world to the part of the universe we cannot see at all, the dark part. The matter that outweighs everything we can touch by 5-to-1, and that nothing we have ever built has managed to detect. Could the Higgs be the bridge to the invisible majority of the universe? There is a job the Higgs does that is bigger than handing out mass, and almost nobody hears about it because it is harder to put on a poster. The Higgs is the reason 2 of the 4 forces of nature look like 2 forces instead of 1. Go back to the very early universe, the first sliver of time after the Big Bang, when everything was hotter than the inside of any star, hot enough that the Higgs field had not yet fallen off its perch. We said that in that era all the particles were massless. There is a second thing that was true in that era, and it is stranger. Electromagnetism and the weak nuclear force were not 2 separate forces. They were a single thing, one unified force, with 4 massless carriers, all interchangeable, all behaving the same way, woven into one symmetric whole. Physicists call it the electroweak force, and in the heat of the early universe, it was as seamless as a single sheet of cloth. Then the universe cooled, and the Higgs field fell, and that single force tore into 2. 3 of the 4 carriers got caught in the falling field and became heavy, became the W and the Z, the short-range carriers of what we now call the weak force, dying off within the width of a proton. The 4th carrier slipped through the field untouched, stayed massless, and kept reaching across infinity. That 4th one is the photon. That is light. The thing your eyes are built to catch, the thing crossing the room right now, is the one piece of the original unified force that the Higgs field happened not to grab. Light and the weak nuclear force are the same force, split in 2 by the Higgs field as the universe cooled. They look nothing alike to us. One lets you see the stars, reaches forever, runs every color and every image and every warm ray of sunlight. The other is locked inside the nucleus, invisible, reaching almost no distance at all, showing itself only in certain radioactive decays. And underneath, before the field fell, they were one. The reason they are different today is not that they were ever truly different. It is that the Higgs field, settling into its valley, chose which carriers to weigh down and which to let go, and that choice is the entire difference between the force that lets you see and the force that lets the sun burn. This is why some physicists describe learning about the Higgs as peeling back a layer of reality. What looks fundamental to us, the clean separation between light and the weak force, is not fundamental at all. It is a consequence of the field we live inside. We were born and raised in a universe where the Higgs field is already switched on, already in its valley, already keeping the photon massless and the W and Z heavy, so we naturally think of light and the weak force as 2 different things, the way a fish born in cold water would think cold was simply what water is. Heat the universe back up, melt the field back to 0, and the distinction dissolves. The 2 forces flow back into 1. And the splitting follows a precise mathematical pattern, the kind of pattern that, once you see it, you cannot unsee. The photon that survives massless is not simply one of the original 4 carriers left alone. It is a specific blend of two of them, mixed in an exact proportion, and that exact proportion is the one and only combination that the fallen Higgs field does not touch. Every other blend gets mass. One blend, one direction in the abstract space of these fields, threads through the condensate without being grabbed, and that surviving direction is electromagnetism. The whole of light, the entire force that runs your vision and your chemistry and the warmth of every star, is the single thread that the Higgs field left hanging free. So when people ask what the Higgs field actually is, the deepest honest answer is not that it is the thing that gives mass. It is that it is the thing that decides which forces are long-range and which are short-range, which carriers are heavy and which fly free, and therefore what the four forces of nature even are. It carved the electroweak force into electromagnetism and the weak force. It set the boundary between the visible reach of light and the buried reach of radioactivity. Mass is one consequence of that carving. The shape of physics itself is the larger one. The separation between the force you see by and the force hidden in the atom's heart is not written into the bones of the universe. It was set, once, in the first moment of cooling, by a field falling off a perch. Run the tape back far enough and that distinction disappears. The light leaving a distant star and the decay ticking inside a lump of uranium are estranged halves of one thing divided by the same event that gave you the mass to exist. Which leaves the question of what else the field might be hiding from us. We know it split the electroweak force. We know it sets the masses of the fundamental particles. But the Higgs we found is, so far, exactly the plain and simple version the theory's earliest sketch allowed, a single particle doing the minimum job with no extra features. And almost nobody believes it is really that simple, because a simple Higgs leaves too many other mysteries untouched. What if the one Higgs we found is not the whole story? What if it is a door, and we have only just noticed the handle? Most of the universe is missing. Not missing in the sense of lost. Missing in the sense that we can measure its gravity, we can watch it bend the paths of stars and shape entire galaxies, and we cannot see it, cannot touch it, cannot make any instrument respond to it except through that pull. For every kilogram of ordinary matter, the matter that makes up you and stars and planets and gas, there are about 5 kilograms of this other stuff. We call it dark matter, and the name is just an admission of ignorance. It means matter we cannot see and do not understand. Whatever dark matter is, it does not interact with light at all, which is why it is dark. It does not feel the electromagnetic force, so it does not reflect or emit or absorb. It passes through ordinary matter almost as if the ordinary matter were not there. Right now, by the best estimates, dark matter particles are streaming through your body and through the Earth itself, billions of them, leaving no trace because they barely interact with anything made of atoms. We are swimming in an ocean of something we cannot feel, that outweighs everything we can. Dark matter is where the Higgs might reach past mass. If dark matter is made of some new kind of particle, that particle has to get its mass somehow. And one natural way for a new massive particle to exist is for it, too, to talk to the Higgs field, to get its mass the same way the known particles do. If that is true, then the Higgs is not just the source of mass for ordinary matter. It might be a shared connection, a meeting point, the one field that both the visible world and the dark world plug into. And that would make the Higgs boson something precious, a possible messenger between the part of the universe we can see and the part we cannot. The way physicists look for this is quietly clever. When a Higgs boson is made in a collision and decays, we know all the ordinary ways it can fall apart, and we can predict how often it should decay into each combination of known particles. If the Higgs sometimes decays into dark matter, those decays would be invisible. The dark particles would fly out of the detector, leaving nothing behind, and we would see the Higgs vanish into apparent nothingness more often than the known decays can account for. So they count. They tally every Higgs decay they can identify, and they check whether some fraction of the bosons are disappearing into channels they cannot see. A Higgs that vanishes too often would be a Higgs leaking into the dark sector, a door standing slightly open. So far, the counting matches the ordinary predictions. The Higgs we found decays the way the simplest theory says it should, into known particles, at the expected rates, with no clear excess of invisible disappearances. Which means either the Higgs does not talk to dark matter, or it does so too rarely for our current machines to catch, or dark matter gets its mass some entirely different way that has nothing to do with the Higgs at all. The door, if it is a door, has not yet been seen to open. But it is one of the few doors we have, and the search continues every time the machine runs. This connects to a larger suspicion that runs through the whole field, the sense that the Higgs we found is too plain to be the end. The version of the Higgs that turned up in 2012 is the bare minimum, the simplest possible thing that does the job, a single particle with no surprises. But almost every deeper theory that tries to solve the other mysteries, the lightness of the Higgs mass, the nature of dark matter, the imbalance between matter and antimatter, predicts that the Higgs should come with company. More Higgs particles. A family of them, heavier ones not yet produced, or a Higgs that is secretly not fundamental at all but made of smaller pieces bound together, the way the proton is made of quarks. In those theories, the boson we found would be just the lightest member of a hidden group, the first room in a building we have only entered. The honest position right now is that we do not know which it is. Every measurement we make of the Higgs is also a test of whether it is the simple lone particle or the first sign of something larger. We measure how strongly it couples to each kind of particle and check whether those strengths match the simple prediction exactly, because any deviation, even a small one, would be a crack through which the larger structure might show. So far, the Higgs has been stubbornly, almost disappointingly, ordinary. It keeps matching the minimal theory. And that itself is a kind of mystery, because the minimal theory leaves so much unexplained that a Higgs which perfectly obeys it feels like finding a key that fits one lock perfectly while a dozen other doors stay shut. What I keep turning over is how much rides on a particle we can only ever glimpse as wreckage. We cannot hold it. We cannot watch it for longer than the briefest flicker before it dies. And yet by studying the exact pattern of how it dies, billions of times over, we are trying to read off whether it is alone, whether it touches the dark universe, whether it is fundamental or built from something smaller. We are doing forensics on a ghost and asking the ghost to tell us about the parts of reality we cannot otherwise reach. To go further into what the Higgs really is, we have to go back to the moment it fell and look closely at the precise shape of the trap it fell into. Because the way the field settled, the exact geometry of its valley, hides a detail that even most short explanations skip, a detail about what happened to the wobbles that should have existed and seem to have vanished. When the field fell, something had to give. And what gave was swallowed by the very particles that became heavy. Picture the energy of the Higgs field as a landscape, a surface where height means energy and the field wants to roll downhill to the lowest point. Before the field fell, it sat at the center, at zero, and the landscape around that center had a very particular shape. It was not a simple bowl with the lowest point in the middle. It was the opposite. The center was a bump, a little hill, and around that central bump the ground fell away into a circular trough, a ring-shaped valley surrounding the peak. The classic picture for this is the bottom of a wine bottle, where the center pushes up and the lowest ring runs all the way around. Some people call it the Mexican hat, for the same reason, the raised crown and the circular brim below. While the field sat balanced on the central bump, everything was symmetric. Every direction around the ring was equally low, equally available. No direction preferred over any other, exactly like the pencil balanced on its tip. But the central bump was unstable. The field could lower its energy by rolling off the peak, down into the surrounding trough. So it rolled. And when it rolled, it had to roll in some direction, into some point along the circular valley, and the moment it picked a point, the symmetry was hidden. Every direction had been equal, and now the field sat at one particular spot in the ring, pointing one particular way, just like the fallen pencil choosing a direction. The detail the short versions skip is the heart of how the W and Z actually got heavy. Once the field is sitting in the circular trough, there are two completely different ways it can wobble, and they are not the same kind of wobble at all. It can wobble in and out, toward the central bump and back down, climbing a little up the inner slope and rolling back. That wobble costs energy, because the walls of the valley rise on either side, and a wobble that costs energy to make is a massive particle. That in and out wobble, the costly one, against the steep wall of the valley, is the Higgs boson. That is the particle we found. It is the field oscillating along the direction where the valley has steep sides, and the steepness of those sides is exactly what sets the boson's mass. But there is a second way to wobble, and it is sneaky. The field can also slide around the circular trough, around the ring, without climbing at all. Because the whole bottom of the trough is at the same height, sliding along it costs nothing. No energy. A wobble that costs no energy to make is a massless particle, and these particular massless wobbles have a name, the Nambu-Goldstone modes, after the physicists who understood them. Any time a field falls and hides a symmetry this way, these free, costless wobbles appear, sliding along the flat bottom of the valley. And the theory said there should be several of them, massless particles riding along the circular trough. Which was a disaster at first, because those extra massless particles are not seen. We do not find a spray of new massless particles sliding around. They are not there. For a while, this looked like it sank the whole idea, a prediction of massless particles that simply do not exist. The resolution is the most elegant move in the entire theory, and it is where the mass of the weak force carriers actually comes from in full. Those costless sliding wobbles do not vanish, they get absorbed. They are eaten by the W and the Z. A massless force carrier, like the ones the early electroweak force had, has a kind of incompleteness to it, a missing way of vibrating that only massive particles possess. A massless particle can only wiggle side to side relative to its motion. A massive particle can also wiggle along its direction of travel, a third way of moving that massless particles are forbidden. And the costless sliding wobbles of the Higgs field are exactly the right thing to supply that missing third wiggle. Each W and Z swallows one of the Goldstone wobbles, and in swallowing it, gains the extra way of vibrating that only massive particles have, and becomes massive. The bookkeeping is exact and strangely satisfying. The wobbles that should have been embarrassing massless particles are not lost and not left over. They become the very heaviness of the weak force carriers. The would-be ghosts are eaten and turned into mass. Nothing is wasted. The field falls, the symmetry hides, the costless wobbles appear, and the force carriers consume them and grow heavy on them. And what is left over, the one costly in and out wobble, is the Higgs boson we eventually caught at the collider. Every piece is accounted for. The missing massless particles and the unexplained mass of the W and Z turn out to be the same thing seen from two sides. This is the level at which physicists actually understand the Higgs, and it is why they wince at the syrup. The mass of the weak carriers is not friction against a field. It is the carriers absorbing the field's free wobbles and thereby gaining a way of moving they did not have before. The whole thing is a transformation of one kind of motion into another, a conversion of would-be Goldstone ghosts into the longitudinal shimmy of a massive particle, all enforced by the exact circular shape of that valley. And the shape of the valley is itself a question. Why that shape? Why a raised center and a circular trough, rather than a simple bowl that would never have fallen, never have hidden anything, never have given anyone mass? The shape of the Higgs potential, the wine bottle profile, is put into the theory by hand, chosen because it produces the world we see, not derived from anything deeper. We know the valley has that shape because we live in a universe where the symmetry is hidden and particles have mass, so the valley must have been the falling kind. But nothing tells us why the field's landscape was built that way in the first place. That gap, the unexplained shape of the valley, connects to the strangest unexplained thing of all about the Higgs. It does not treat all particles equally. It grabbed the carriers and gave them enormous mass. It gave the top quark a mass about equal to an entire atom of gold. It gave the electron a mass almost 10,000 times smaller. It gave the lightest particles masses so tiny we can barely measure them. The same field, the same valley, the same fall, and yet the masses it handed out span a range of trillions to one in a pattern with no apparent logic. Why does the Higgs touch each particle by a different amount across a range so vast it has no explanation? That ladder of masses is the next thing to climb. The Higgs field gives mass to the fundamental particles, but it does not give them all the same mass, and the spread is staggering. The heaviest fundamental particle, the top quark, weighs about as much as an entire atom of gold, a single-point particle as heavy as a nucleus of 79 protons and over 100 neutrons. The lightest particles with mass, the neutrinos, weigh so little that we have never even managed to measure their mass directly, only to prove it is not quite zero. Between the top quark and the neutrino, the masses spread across a factor of something like 1 trillion. Same field. Same fall. Same valley. And the masses it hands out range over 12 orders of magnitude with no pattern anyone has cracked. The way this works in the theory is that each particle is connected to the Higgs field by its own personal dial, a number that says how strongly that particle feels the field. Turn the dial high, and the particle gets a large mass. Turn it low, and the particle stays light. The top quark's dial is turned almost all the way up, nearly to the maximum the theory allows. The electron's dial is turned to a tiny fraction of that. The neutrino's dial is turned so low it is almost off. And here is the uncomfortable thing. Every one of those dials is put in by hand. We measure each particle's mass, we work out what its dial setting must be to produce that mass, and we write the number down. We do not predict it. We do not derive it. There is no equation that says the top quark should feel the Higgs so strongly and the electron so weakly. The values are simply read off from reality and inserted. The Standard Model, our best and most tested theory of particles, contains around 20 numbers that have to be measured and put in by hand because nothing explains them, and most of those numbers are exactly these dials, the strengths with which each particle grips the Higgs field. The theory tells you how the Higgs gives mass. It does not tell you why it gives the masses it does. The pattern of the ladder, the specific rungs, the vast gaps between them, is just an experimental fact with no theory behind it. And the pattern is not random looking in a comforting way. It has a strange near order to it that teases. The fundamental matter particles come in 3 copies, 3 families, identical in every way except mass. There is the electron, and then a heavier copy called the muon, and then a heavier copy still called the tau, each one a near-perfect duplicate of the electron but more massive, climbing the ladder by large steps. The quarks do the same, 3 families, each heavier than the last. 3 rungs, repeated across every kind of particle, each family a scaled-up echo of the one below. Nobody knows why there are 3, not 2, not 4, not 17. 3 families, each gripping the Higgs more tightly than the last, for no reason we can find. The universe could apparently have run on just the lightest family. The other 2 seem almost redundant, heavier versions of particles we already have, present in the early universe and in collisions, but playing little role in the ordinary matter around you. When you ask a physicist why there are 3 families and why their Higgs dials are set the way they are, the honest answer is a shrug dressed in mathematics. We have measured it. We cannot explain it. It is one of the clearest signs that the Standard Model, for all its triumph, is not the final theory but a layer over something deeper, because a final theory should not need 24 numbers handed to it from outside. It should grow them from within. The Higgs revealed the mechanism of mass, and in the same breath exposed how little we understand about the values of mass. There is a thread worth pulling here about the top quark in particular, because its dial is turned so close to the maximum that it almost looks deliberate. The top quark feels the Higgs more strongly than anything else, right up near the edge of what the theory permits, and that near maximal grip is one of the numbers that decides whether our vacuum is stable or sits on that metastable ledge we talked about. The reason we are perched at the boundary between a safe universe and a slowly decaying one comes down, in large part, to the exact strength of the top quark's connection to the Higgs. If that one dial were set a little differently, the vacuum would be comfortably stable or comfortably doomed. Instead, it sits at the edge, and we do not know why the dial landed there. So the ladder of masses is not a solved detail. It is a wide-open question wearing the costume of an answer. We can tell you that mass comes from the Higgs. We cannot tell you why your electrons are as light as they are, why the top quark is as heavy as it is, why there are 3 families climbing the same rungs, or why the heaviest particle's grip on the field sits right at the value that balances the whole universe on a knife edge. The discovery gave us the machine of mass and withheld the blueprint. What the discovery did give us, though, is a way to reach back to the moment all of this was set. The fall of the Higgs field was an event in the history of the universe, a real moment in real time, a transition the cosmos passed through as it cooled. And like any transition, it may have left marks. The early universe did not just quietly switch the field on, it went through a transformation. And that transformation might be tangled up with one of the oldest mysteries of all, the reason there is any matter here for the Higgs to give mass to in the first place. Why is there something rather than nothing in the most literal physical sense? The fall of the Higgs may have had a hand in it. Everything we have talked about, the field switched on everywhere, the particles given mass, the weak force cut short, all of it traces back to a single transition in the early universe, when the cosmos cooled past the point where the Higgs field could no longer stay balanced at 0 and fell into its valley. This was not a gentle, eternal fact. It was an event. It happened at a particular moment, a tiny fraction of a second after the Big Bang, when the universe had expanded and cooled just enough for the central bump to become unstable and the field to roll off it. Before that moment, a symmetric universe of massless particles and one unified electroweak force. After it, the universe we recognize, with mass and split forces and the possibility of matter clumping together. Physicists call this the electroweak phase transition, and the word transition is doing real work because it is the same kind of thing as water freezing into ice. When water freezes, it does not cool smoothly forever. It reaches a point and changes state, abruptly, into something with different properties. The Higgs field freezing into its valley was the universe-changing state, the vacuum itself crystallizing from a symmetric form into the form we live in now. And just as ice forming in water can trap bubbles and leave structures behind, the freezing of the Higgs field may have left its own marks on the universe, depending on exactly how the transition happened. And this reaches back to the oldest question there is. Look around at everything, the stars, the planets, your own body. It is all made of matter. There is essentially no antimatter, the mirror image version of every particle, anywhere in the natural universe. And yet our best understanding says the Big Bang should have made matter and antimatter in equal amounts. Equal amounts that should then have met and annihilated each other completely, leaving a universe of pure light and nothing else. No stars. No matter. No Higgs giving mass to anything, because there would be nothing for it to give mass to. The fact that you exist means that somehow, in the early universe, a tiny imbalance appeared, a slight excess of matter over antimatter, about one extra particle of matter for every billion matter-antimatter pairs. Those pairs annihilated, and the 1 in a billion left over is everything. You are made of the survivors. All the matter in the universe is the small remainder that had no antimatter partner to annihilate with. What created that imbalance is one of the great unsolved problems, and the electroweak phase transition is one of the leading suspects. Under the right conditions, the moment the Higgs field fell could have been violent enough, abrupt enough, to tip the balance, to favor matter over antimatter by exactly the needed sliver. If the transition happened sharply, with bubbles of the new fallen vacuum forming and expanding and colliding, the boundaries of those bubbles could have acted as the sites where the imbalance was frozen in, matter accumulating on one side as the new vacuum swept through. In that picture, the same event that gave particles their mass also decided that there would be particles at all, that the universe would not annihilate itself into empty light. For this to work, though, the transition had to be a particular kind. It had to be sharp, a sudden snap from one state to the other with bubbles forming, rather than a smooth, gradual slide. And when physicists take the Higgs mass we actually measured and work out what kind of transition our universe would have had, the answer comes back disappointing for this story. With a Higgs of about 133 proton masses, the transition looks like it was smooth, gradual, a gentle crossover rather than a sharp snap with bubbles, which means the simplest version of the Higgs probably did not, on its own, create the matter imbalance after all. The numbers do not quite cooperate. Either there is more to the Higgs than we have found, extra particles or extra structure that would have sharpened the transition, or the imbalance came from somewhere else entirely, some other process in the even earlier universe that we have not identified. So once again, the Higgs leads us to the edge of a mystery and then declines to solve it. It points at the matter-antimatter imbalance. It offers a mechanism that ashudni matter, maybe measured value of its own mass, takes that mechanism off the table, or at least demands that something else be added. This keeps happening. The Higgs is the particle that answers the question it was built for, and then hands you three larger questions it cannot close. Why is its mass so small? Why is the vacuum perched at the edge of stability? Why does it grip each particle so differently? Why did the matter survive? It is less a final answer than a doorway that, once opened, reveals how many doors are still shut. And yet none of these open questions take away from what was actually accomplished, what was actually confirmed. The field is real. We prove that empty space really is filled with something, really does carry a value everywhere, really does ring when struck. That much is no longer a guess. A young man wrote it down in 1964, and a room full of people confirmed it in 2012, and an old man wiped his eyes because the strangest idea of his life had turned out to be how the world is built. There is one place left to take all of this, and it is the place we started. Out of the early universe and the colliders and the wine bottle valleys and the unsolved ladders of mass, back to the one piece of the universe you have direct access to right now. The body lying in the dark, made of atoms that only hold together because a field fell off its perch 14 billion years ago and never got back up. What does all of this actually mean for the matter you are made of, tonight, in this room? Behind that single morning in 2012 stand decades of patient failure, and they are part of what the discovery means. The collider that found the Higgs was not the first machine to look for it. For decades before, physicists had been hunting, and the hunt is a story of near misses and dead ends and a kind of self-imposed discipline that is rare to see anywhere. The trouble was always the same. The theory could not predict the mass of the boson, so nobody knew where to look. The Higgs could have been light enough to find in the 1980s or heavy enough to stay out of reach for another century. So the search had to crawl up the mass range, machine by machine, ruling out one region at a time, never knowing if the next region held the prize or if the prize was still far above. Each new collider could reach a little higher in energy, and each one looked, and for a long time each one came back empty, which only meant the boson, if it existed, was heavier than that machine could reach. In the same underground tunnel that now holds the Higgs discovery machine, an earlier collider ran through the 1990s, smashing electrons and their antimatter twins together instead of protons. In its final months, as it was being pushed to its absolute limit before being dismantled to make way for the bigger machine, it saw a few tantalizing hints, a handful of events that looked like they might be the edge of a Higgs signal at the very top of its reach. The physicists running it begged for more time, a few more months to chase the hint. The hint was not strong enough to be sure. The decision was made to shut the machine down on schedule and build its successor. Whether those few events were the first whispers of the real Higgs, glimpsed years early at the very edge of an older machine's power, or just noise dressed up as hope, we will never know for certain. The machine that could have settled it was already being taken apart. Across the ocean, another collider spent years in the 2000s narrowing the range from a different direction, smashing protons and antiprotons, slowly squeezing the space where the Higgs could hide, ruling out band after band of mass. It never quite reached the discovery, but it tightened the noose, and by the time the big European machine turned on, the search had been funneled down to a narrow window where the Higgs almost had to be, if it was anywhere. The window was low, in the range where the Higgs is hardest to see, buried in the most background, which is a particularly cruel place for it to have been hiding. The easiest places to look had all come up empty. The boson was waiting in the hardest one. And then there is the discipline, which I find more impressive than the machines. When you are searching for a tiny bump in a sea of noise, the greatest danger is not the noise. It is you. It is the human tendency to see the pattern you are hoping for, to nudge a cut here and a selection there, unconsciously, until the noise arranges itself into the shape of your wish. Physicists know this about themselves, and they build a defense against their own hope. They run what is called a blind analysis. They design the entire search, fix every choice about how to filter and count the data, and lock it all in place before they are allowed to look at the region where the signal would appear. They tune their methods on everything except the answer. Only when the whole procedure is frozen, when they can no longer adjust anything, do they unblind, do they finally look at the part of the data that could hold the Higgs. By then, it is too late to fool themselves. The choices were made in ignorance of the outcome. That is why two teams could stand up on the same morning and present the same bump. They had each searched independently, each kept blind to the other, each frozen their methods before looking, precisely so that neither hope nor knowledge of the other team could pull them toward a wished-for answer. When both teams, having tied their own hands, found the same particle at the same mass, the result was as close to unfoolable as human beings have ever made a measurement. The discovery was not just a triumph of engineering. It was a triumph of not trusting yourself, of building elaborate machinery to prevent your own desire from contaminating what you see. There is something quietly moving in that, in a community of people who wanted this answer more than almost anything, spending decades constructing ways to stop themselves from believing it too easily. The Higgs was the most sought-after particle in the history of the field, and the people who sought it trusted themselves with it least of all. They earned the certainty. They did not assume it. And when the certainty came, it did not end the work. It started a new and stranger phase, because finding the Higgs was only the first question. The deeper question was whether the Higgs we found behaves exactly the way the theory says it should, or whether, in the fine details of how it acts, it hides a difference that would crack the whole picture open. How do you keep interrogating a particle you have already discovered? Finding the Higgs told us the field is real. It did not tell us whether the field's valley has exactly the shape the theory drew, and that shape is the next frontier, because the shape of the valley is the part of the Higgs we have barely touched. Remember that the Higgs boson is the field wobbling in and out against the steep wall of its valley. The steepness of that wall sets the boson's mass, and we have measured the mass, so we know the steepness at the one point where the field is sitting. But a valley has a whole shape, not just a steepness at the bottom. It curves. It rises. The full profile of the Higgs potential, the entire wine bottle landscape, is what we would need to know to truly say we understand the field. And we have only measured a single point on it, the very bottom, the place where the field rests now. The rest of the curve, the way it bends as you move away from the bottom, is still almost entirely unmeasured. There is a way to probe the shape, and it is one of the hardest measurements anyone has ever attempted. The shape of the valley determines how strongly the Higgs field interacts with itself. A Higgs boson can, in principle, interact with another Higgs boson because they are both wobbles of the same field, and the field's own landscape decides how strongly those wobbles push on each other. If you could make two Higgs bosons at once, in the same collision, and measure how often they appear together and how they affect each other, you would be reading off the curvature of the valley away from its bottom. You would be measuring the field's relationship with itself, which is the same as measuring the shape of the trap it fell into. The problem is that making two Higgs bosons at once is fantastically rarer than making one, and making one is already a 1 in a billion event. Producing a pair is so rare that even after years of running, only a handful of candidate events trickle in, far too few to say anything precise yet. So the shape of the valley remains, for now, mostly a theoretical drawing. We assume it has the wine bottle form because that form produces the world we see, but we have not directly traced the curve. We have confirmed there is a bottom. We have not yet mapped the slopes. This is why physicists are already planning machines beyond the current one. Larger rings, higher energies, or entirely different designs that would collide electrons instead of protons to make cleaner, less cluttered Higgs events. The dream behind these machines is not to find the Higgs again. It is to make Higgs bosons by the millions, in clean conditions, and finally measure the field's self-interaction, finally trace the shape of the valley, finally check whether the landscape really has the form the theory assumed, or whether it bends in some unexpected way that would point to all the deeper physics we suspect is hiding. The shape of that valley is tied to everything left unsolved, to the stability of the vacuum, to the matter imbalance, to the lightness of the Higgs mass. Mapping it would be like finally getting to read the part of the book we have only seen the cover of. It is a strange situation to be in. We have a particle, confirmed, celebrated, the subject of a Nobel Prize and 1,000 headlines, and we still do not know the shape of the thing it is a wobble of. We know it wobbles. We measured how fast it wobbles at the bottom. We have not measured the walls. The Higgs, more than a decade after its discovery, is still mostly unexplored, a confirmed existence with an unmapped interior, and the people who study it talk about the coming measurements the way earlier generations talked about the discovery itself, as the thing that might finally crack the door to what lies underneath the standard model. What keeps me on this is the patience it demands. The discovery took 50 years. Mapping the valley may take 50 more, across machines not yet built, by physicists not yet born, chasing a curve that the people who first imagined the field will never live to see traced. It is a relay measured in lifetimes, each generation handing the next a slightly sharper picture of a landscape no one can ever look at directly, only infer from the wreckage of collisions. And underneath all of it, under the valleys and the colliders and the careful measurements, there is the plainest and most disorienting fact of the whole story, the one we have circled the entire time without quite staring at. The thing we found is not a particle in the way you picture a particle. It is evidence that what you have been calling empty is not empty, has never been empty, cannot be empty. What does it actually mean that the nothing around you is full? Take everything out of a box. Every speck of dust, every molecule of air, every stray particle. Pump it down to the hardest vacuum any laboratory can make, better than the space between the stars. What is left in the box? The honest answer, the one the Higgs forces on us, is that the box is still full. It is full of fields. The electron field is there, sitting at its quiet zero, ready to be plucked. The electromagnetic field is there. And the Higgs field is there, not at zero but at its fallen value, switched on, holding the same non-zero value it holds everywhere, in the box and in your chest and in the deepest void between galaxies. You cannot pump out the Higgs field. There is no valve for it. It is not in the box. It is the box. It is a property of space itself. The particle is almost the least of it. The real discovery is that empty space has structure. The vacuum is a medium, a substance, a thing with properties, and those properties decide what can exist inside it. The masses of particles, the reach of forces, the very distinction between light and the weak force are not properties of the particles alone. They are properties of the space the particles live in, set by the value the Higgs field happens to hold here. Change the value of the field, and you change the rules. The particles would be the same particles. The vacuum they swim in would be different, and so everything built from them would be different too. We tend to think of empty space as the stage, the neutral backdrop, the nothing against which the something happens. Particles are the actors, space is the empty theater, and the theater does not affect the play. The Higgs erases that line. The theater is not empty, and it is not neutral. The stage is made of the same kind of stuff as the actors, fields layered on fields, and the stage reaches into the actors and tells them how heavy to be, how far to reach, what they are allowed to do. There is no clean separation between the contents of the universe and the space that contains them. The container is a participant. The nothing is doing something, constantly, everywhere, to everything. And the something it is doing is not gentle bookkeeping. It is the reason matter can exist. We have said this from several directions now, but here it lands at its plainest. If the Higgs field sat at 0 instead of its fallen value, if the vacuum were truly empty in the way our intuition wants, then electrons would be massless, racing at the speed of light, never able to slow down, never able to be caught into orbit around a nucleus. There would be no atoms. The fundamental particles would all fly at light speed forever, scattering off each other, unable to ever bind, unable to ever rest. A truly empty vacuum is a sterile one. It is the fullness, the field switched on, that lets things slow down enough to become things. Emptiness, the real kind, would be lethal to existence. We owe our being to the fact that space is not empty. This reframes the question people usually ask. They ask why the Higgs gives particles mass, as if mass were an addition, a feature granted to particles that could have gotten along without it. But from inside the full vacuum, it is the other way around. Mass is the default state of a particle living in our switched-on universe. Masslessness is the exotic condition, the thing that requires special escape, like the photon threading through the one direction the field does not grab. To have mass is simply to be a particle existing in the medium of our vacuum, feeling the field that is always there. The question is not why most particles are massive. The question is how the photon manages not to be. I keep returning to the word nothing because the Higgs quietly destroyed it. There is no nothing, not in our universe, not anywhere we can reach. The most empty place imaginable is a place full of fields holding their values, the Higgs among them, shaping whatever passes through. When you look up at the dark gaps between the stars and think you are seeing emptiness, you are seeing the most pervasive substance in existence, the field that fills everything, the one thing you can never escape because it is not in space, it is space. The dark between the stars is not empty. It is the same full vacuum that fills the space between your own atoms, the same field that is, right now, the reason those atoms hold. Which brings the whole long journey down to the smallest and nearest place it can land. Not the early universe, not the colliders, not the valleys and the dark matter and the unsolved ladders. Just the matter directly beneath your own attention, the body. The atoms that are, at this moment, holding their shape only because the vacuum they sit in is full. Let us go there, finally, and stay. The Higgs gives the fundamental particles their intrinsic mass, the small intrinsic mass that an electron or a quark carries on its own. And the strong force, through trapped energy, gives the proton and the neutron almost all of their mass, the 99% that is binding energy frozen by Einstein's equation. Two sources, two kinds of mass, both real. But underneath both of them is a single deeper idea. And it is the idea we started with, all those hours ago, when we talked about pushing a stalled car on a flat road. Inertia. The resistance of a thing to being pushed. The deepest version of what mass is ties both sources together. Mass is energy stuck in place. Energy that cannot move freely, that is bound, confined, locked into a small region instead of streaming away. A photon's energy moves at the speed of light and never holds still, and a photon has no mass. The energy of the strong force inside a proton is trapped, bound, churning in a tiny volume unable to escape, and that trapped energy is mass. The energy an electron carries through its interaction with the Higgs field is, in its own way, energy that cannot simply fly off at light speed. Energy tied to the particle as it sits in the full vacuum, and that tying is mass. In every case, the same principle. When energy is free to move, it is massless and races. When energy is bound, when it is held in place, it has mass, and it resists, and it can rest. Mass, then, is not a substance. It is not stuff added to particles. It is the name we give to energy that has been pinned down, trapped, made to sit still, whether by the strong force squeezing quarks into a proton or by the Higgs field gripping an electron in the vacuum. Your mass is the energy of your existence held in place. The weight on the scale is energy that cannot escape, frozen into the shape of you, and the freezing is done partly by the strong force and partly, for the fundamental particles, by the field that fills all space. This is why the syrup picture is not just slightly wrong, but wrong at the root. Syrup adds drag, a force that resists motion through it. Mass is not resistance to motion. A thing with mass, once moving, moves forever, freely, with nothing pushing back. Mass is resistance to a change in motion, which is a completely different thing, and it comes not from pushing through a medium but from energy being bound in place. The Higgs does not slow particles down. It binds a certain amount of energy to them, in the form of their intrinsic mass, by their interaction with the full vacuum, and that bound energy is what resists when you try to change what the particle is doing. The stubbornness you would feel pushing a heavy object, the resistance of your own body to being suddenly shoved, the weight that holds you against the bed right now, all of it is energy that has been trapped into matter and refuses to be moved without a fight. Some of that trapping is the strong force raging in the cores of your atoms. A small but load-bearing fraction of it is the Higgs field, switched on everywhere, gripping the fundamental particles, set into its valley 14 billion years ago and never released. The resistance is not abstract. You can feel it whenever you lift anything, whenever you turn over, whenever you feel the simple downward pull of your own body. That feeling is energy bound into matter by fields. That feeling is the Higgs, in part, made flesh. So we have arrived, by the long way around, at something you can actually sense. Not a particle in a collider. Not a curve on a graph. The plain weight of yourself, lying still, which is the most ordinary sensation there is, and which turns out to be one of the few places where the deepest structure of the universe touches you directly enough to feel. That weight has a history, though, longer than the universe has had stars. The idea that energy bound in place becomes mass did not arrive whole. It came from a winter of work in the 1950s and 60s, from people staring at frozen metals and arguing about whether the same trick could possibly apply to all of space. To understand what the Higgs is, it helps to know who first dared to think the vacuum could behave like a superconductor, and why their colleagues thought they were wrong. The Higgs field did not appear in a single flash of insight from a single mind. It was assembled, slowly, by people working on what looked like an unrelated problem, and the path from that problem to the structure of the vacuum runs through some of the most stubborn arguments in 20th century physics. It begins, again, with superconductivity, but with the deep theory of it rather than the bare fact. In the late 1950s, Three physicists finally explained why certain metals lose all resistance when cooled. The explanation, which took decades to find, was that the electrons pair up and condense into a single coordinated state, the ocean we described earlier. But buried in that explanation was a mathematical feature that troubled a physicist named Yoichiro Nambu. He noticed that the superconducting state had hidden a symmetry, the same kind of symmetry hiding we later needed for the Higgs, and that this hiding came packaged with the appearance of certain low-energy wobbles, the costless slides along the flat valley that would later be called Goldstone modes. Nambu did something bold. He took this idea, which had been developed to explain a cold lump of metal, and asked whether the same mathematics could describe fundamental particles. Whether the masses of particles in the universe might come from a hidden symmetry in the vacuum, the same way the behavior of a superconductor came from a hidden symmetry in the metal. He was, in effect, the first to seriously suggest that empty space might be doing what a superconductor does. For this line of work he would, much later, receive a Nobel Prize of his own, because it turned out to be one of the foundational ideas of all modern physics. A physicist named Jeffrey Goldstone proved a theorem, a piece of mathematics so clean it seemed inescapable. He showed that whenever you hide a symmetry this way, you always get those costless wobbles, and the costless wobbles are massless particles. Always. No exceptions. The theorem seemed airtight. And that was a disaster, because it meant that any attempt to give particles mass by hiding a symmetry in the vacuum would also produce a swarm of massless particles that nobody had ever seen. The cure came with a side effect worse than the disease. You could hide a symmetry to make mass, but you would flood the universe with massless ghosts that do not exist. For a while, this stopped everything. The theorem said, you could not have the mass without the ghosts, and the ghosts were not real, so the whole idea of mass from a hidden symmetry seemed dead on arrival. Some of the best physicists in the world believed the door was closed. The physicist who saw the crack in the door was Philip Anderson, the same Anderson who understood the photon gaining mass inside a superconductor. He pointed out something that the elegant theorem had quietly assumed away. The theorem was proven for fields on their own, in isolation. But inside a real superconductor, the relevant field is not on its own. It is coupled to electromagnetism, to the photon. And when you include that coupling, something the pure theorem did not account for happens. The costless ghost wobbles and the massless photon find each other and combine, and the result is not a massless ghost plus a massless photon. The result is a single massive particle. The ghost gets eaten. The photon gets heavy. The theorem's prediction of massless ghosts is evaded, not by breaking the theorem, but by stepping outside the conditions it assumed. Anderson said this, in print, in 1963, about superconductors. He even suggested it might matter for particle physics. But he said it in the language of condensed matter, the language of metals and electrons, and he did not write down the full relativistic equations that particle physicists would accept. So his insight sat there, correct, published, and largely ignored by the particle physicists who needed it most, because it was written in the wrong dialect and made claims about the universe based on the behavior of cold metal, which sounded to many like a stretch too far. It took until 1964 for people to write the idea in the proper language of particle physics, fully relativistic, airtight, undeniable. That is when Brout and Englert, and Higgs, and Guralnik and Hagen and Kibble, independently, did the thing Anderson had gestured at, but did it rigorously, for the fields of particle physics, showing precisely how a hidden symmetry coupled to force carriers gives those carriers mass while the ghosts are eaten, They closed the loophole in Goldstone's theorem for good and showed the universe was allowed to do exactly what a superconductor does. So the idea we now name after one man was really the work of a whole winter of minds, building on a theory of frozen metal, fighting through a theorem that seemed to forbid it, rescued by a condensed matter physicist whose insight was ignored for being in the wrong language, finally written down in rigorous form by 6 people in a single year, and then waiting half a century for proof. The reason it carries Higgs's name more than the others is partly that one extra sentence about the particle, and partly the accidents of how names stick. The reason it carries any of their names rather than Anderson's or Nambu's is the long history of which insights get remembered and which get buried under the wrong vocabulary. There is something honest about knowing this, about seeing that the cleanest ideas in physics are rarely clean in their making. They come out of arguments and dead ends and theorems that seem to forbid the very thing that turns out to be true. The Higgs field was not discovered. It was wrestled into existence over a decade by people who mostly thought they were working on something else. And the something else, the superconductor, keeps pulling us back, because it is not just a historical stepping stone. The resemblance between the vacuum and a superconductor is so exact that it raises a question we have not yet asked directly. If empty space behaves like a superconductor, then in what sense is the difference between full space and empty space, like the difference between a warm metal and a cold one? Could the vacuum in principle be melted? What would it take to melt the vacuum, and has the universe ever been melted before? A superconductor is only a superconductor while it stays cold. Warm it past its critical temperature, and the paired electrons break apart. The condensate dissolves, the resistance returns, and the metal becomes ordinary again. The hidden symmetry comes back out of hiding. The special state melts. This is not a strained analogy for the Higgs. It is the same physics, and it means the Higgs vacuum can melt too, given enough heat, and it tells us something concrete about the history of everything. Heat is just energy of motion, particles jostling harder the hotter things get. When the jostling is violent enough, it can shake a hidden symmetry back into the open, the way heat shakes apart the electron pairs in a warming superconductor. For the Higgs field, the critical temperature is staggeringly high, hotter than the center of any star, hotter than almost anything in the present universe. But the early universe was that hot. In the first tiny fraction of a second after the Big Bang, the whole cosmos was far above the Higgs critical temperature, and in that heat, the Higgs field could not stay fallen. The jostling was too violent. The field sat at zero, balanced on the central bump, symmetry unhidden, all particles massless, the electroweak force unified. The vacuum was melted. Not as a figure of speech. As a real thermodynamic state the entire universe was in. Then it cooled, as it expanded, the way a gas cools as it spreads. And at one specific moment, when the temperature dropped through the critical point, the vacuum froze. The Higgs field fell into its valley everywhere, the symmetry hid, particles gained mass, the forces split. This is the electroweak phase transition we mentioned before, but now you can see what kind of event it really was. It was the universe freezing, the vacuum crystallizing from its melted symmetric state into the frozen state we live in. The same way water freezes into ice at a particular temperature, the same way a metal becomes superconducting at a particular cold. So the universe has been melted before. For the first sliver of its existence, the Higgs field was switched off. The vacuum was in its hot symmetric phase, and there was no mass, no atoms, no possibility of structure. Everything we are made of waited on the far side of a freezing event that had not happened yet. We are, in a sense, living in frozen time, in the crystallized vacuum that formed when the universe cooled enough for the field to fall. Before that freezing, the universe was a different kind of place, ruled by different effective laws, and we can never get a direct look at it because no atom, no light as we know it, no structure could exist there to carry a record forward. The collider does something close to mythological here. When two protons crash together at very nearly the speed of light, the energy concentrated at the collision point for the briefest instant in the smallest volume reaches temperatures comparable to that early melted era. In that pinpoint flash, the conditions of the universe before the freezing are recreated, just for a moment, just in a space smaller than an atom. The collider is not only a microscope, it is a furnace that briefly melts a speck of the present vacuum back to the state it was in before the universe froze. The Higgs bosons it makes are ripples shaken loose, precisely because that speck of space has been heated back across the line, back toward the symmetric phase, where the field can be made to ring. This reframes the whole achievement once more. We did not just find a particle. We learned to briefly reverse the oldest freezing in existence, to warm a fleck of space back toward the melted state it occupied in the first instant of time, and to watch what shakes loose. The discovery was, in a strange and literal sense, a glimpse of the universe before it became the kind of universe that can contain us. We made a tiny, momentary patch of the early cosmos, the cosmos without mass, and read its echoes in the wreckage. The vacuum we live in froze once, into the state it is in now. We discussed earlier that this state may be metastable, a ledge rather than the true bottom. Put the melting and the metastability together, and you get something to think about. The freezing that made our world may not have been the final freezing. The vacuum could, in principle, freeze again someday, far in the unreachable future, tunneling into the deeper valley and crystallizing into a new state with different laws. The universe froze once to become the place we know. Whether it has finished freezing, or is merely paused on a ledge between one frozen state and a deeper one, is a question that depends on numbers we are still measuring, balanced on the same knife edge as everything else about the Higgs. The vacuum around you is frozen, stable on every timescale that will ever matter to anything that exists, and it froze into exactly the state that allows you to be here. The melting is ancient history. The refreezing is impossibly distant, and in between sits this long, quiet era of crystallized vacuum, the era of atoms, the only era in which a body could lie still in the dark and wonder about any of it. The machine that melted that speck of vacuum to find the Higgs has a scale that is hard to hold in the mind. To recreate the heat of the early universe in a controlled way, thousands of people across decades built something that has no equal in the history of engineering, and the sheer physical facts of it tell you how badly the species wanted this answer. The ring is about 27 kilometers around, roughly the size you could walk in an afternoon, buried about 100 meters underground beneath farmland and towns and the border between two countries. Inside it run two pipes, and inside those pipes is a vacuum emptier than the space between the planets, because the protons racing through must not hit a stray molecule of air. Around the pipes sit thousands of magnets, enormous ones, that bend the proton beams around the circle, and those magnets only work if they are colder than outer space. To get them that cold, the machine is bathed in liquid helium, tons of it, chilling the magnets to within about 2 degrees of the lowest temperature that can exist, colder than the background of the universe itself. So in the same machine you have the coldest extended region in the known cosmos, the magnets near absolute zero, and at the collision points, for an instant, some of the hottest conditions since the Big Bang. The coldest and the hottest separated by a few meters in a ring under a quiet countryside. The protons inside are pushed to a speed so close to light that the difference is almost not worth stating. They go around the 27-kilometer ring more than 11,000 times every second. They are bunched into tight packets, and the packets are steered to cross through each other 40 million times a second at the centers of the great detectors. Each crossing sends hundreds of billions of protons through hundreds of billions of others, and out of all that, only a handful actually collide head-on because protons are so small and mostly empty that direct hits are rare even when you fire them in their billions. The detectors that watch the collisions are the size of buildings. One of them is tall enough to fill a cathedral, wrapped in layer after layer of sensors, each layer measuring something different about the spray of particles flying out of the collision, tracking their paths, measuring their energy, identifying what they are. When a collision happens, the debris flies outward through these layers, and each layer records its passage, and from those records the path and energy of every fragment is reconstructed. The amount of information is beyond anything. The collisions happen so fast and so often that the detectors generate more raw data than any system could ever store. So most of it is thrown away in real time, in millionths of a second, by automated systems that decide on the fly which collisions look interesting enough to keep. Only a tiny fraction is saved. The Higgs, when it appears, must appear in the fraction the machine chooses to remember, which means the search depends on having taught the machine in advance what kind of event might be worth keeping. And behind the steel and the helium and the data are the people. Thousands of them, from scores of countries, who built this across decades, many of whom devoted their entire working lives to one piece of one detector, who would never personally see the particle, and could only contribute one careful component to a search far larger than any individual. Physicists who calibrated one type of sensor for 10 years. Engineers who designed the cooling for one section of magnets. Students who wrote the code that decides, in a millionth of a second, whether a collision is kept or discarded. The discovery was announced by 2 teams, but each team was thousands of people, and the names on the papers run to pages, because no one person built this and no one person found the Higgs. It was found by a collaboration on a scale that has few parallels in any human endeavor, science or otherwise, a coordinated effort by thousands of people across a generation to ask the universe one specific question and be patient enough to hear the answer. What strikes me about it is the ratio. All of that, the largest machine ever built, the coldest place in the cosmos, decades of thousands of lives, the most data ever handled, to catch the faint echo of a particle that exists for less than a billionth of a trillionth of a second and can never be seen directly. The effort is almost absurdly out of proportion to the size of the thing it sought. And yet the thing it sought is the reason matter can exist, so the proportion is exactly right. We spent a generation and a continent's worth of engineering to confirm that empty space is full, and it was worth it, because the alternative was not knowing whether our entire picture of why we can exist was true. That picture, the one the machine confirmed, reaches all the way up from the collider to the sky, to the sun, to the light that warms your skin in the morning. Because the same field, the same fallen Higgs, has its fingerprints on the way the sun burns. The sun is a fusion furnace, and the simplest thing to say about it is that it crushes hydrogen into helium and releases energy. But the first step of that process, the very first thing that has to happen before anything else, runs through the weak force, which means it runs through the Higgs, and the consequence is one of the most quietly important facts about why you are alive. To fuse hydrogen, the sun has to start by bringing 2 protons together. But 2 protons cannot simply stick. To make the first building block on the road to helium, one of those 2 protons has to turn into a neutron at the exact moment they meet, because only then can they bind into a stable pair. Turning a proton into a neutron is a job for the weak force. It is precisely the kind of particle transformation that nothing but the weak force can do. So the very first step of the chain that lights the sun depends on the weak force reaching in and converting one particle into another at the instant of collision. And the weak force, as we have spent hours establishing, is feeble and short-ranged because the Higgs field gave its carriers enormous mass. This is the part that turns out to be a strange kind of blessing. Because the weak force is so weak, that first conversion of a proton into a neutron almost never happens. When two protons collide in the core of the sun, the overwhelmingly likely outcome is that they simply bounce apart, unchanged, because the weak force is too feeble to convert one of them in the brief instant they are close. A given proton in the sun's core can wait, on average, billions of years before it successfully undergoes that first fusion step. Billions of years. The reaction is so reluctant that each proton waits a time comparable to the age of the Earth before it fuses. That reluctance is why the sun lasts. If the weak force were stronger, if the Higgs had given its carriers less mass and let it reach further, that first step would happen easily, and the sun would fuse its hydrogen in a flash, burning through its fuel in a geological eye blink, flaring and dying long before any planet could cool, long before any chemistry could slowly assemble life. The feebleness of the weak force, inherited directly from the heaviness the Higgs handed its carriers, is what stretches the sun's life from an instant into the billions of years that give a planet time to grow life and keep it. The sun burns slowly because the weak force is weak, and the weak force is weak because the Higgs field fell and made its carriers heavy. So there is a direct line, an unbroken causal thread, from a field falling off a perch in the first fraction of a second after the Big Bang, to the heaviness of the weak force carriers, to the reluctance of the sun's first fusion step, to the slow, steady warmth that has fallen on this planet for billions of years and made everything that lives. The light on your skin in the morning is metered out at exactly the rate it is because of how heavy the Higgs made three particles you will never see. Turn the dial that sets their mass, and you change how fast the sun burns, and a faster sun is a dead one for our purposes, gone before life could begin. The Higgs is not a remote curiosity confined to colliders and the first instant of time. Its choices reach all the way up to the sky and meter the warmth of an ordinary morning. The same property that makes the weak force buried and invisible in the atom is the property that keeps the sun from burning out, which means the Higgs is quietly woven into the length of a day, the length of a year, the slow, patient time scale on which a world can become habitable. We do not feel it as the Higgs. We feel it as the sun being there, reliably, warm, the same tomorrow as today. But underneath that reliability is a feeble force, and underneath the feebleness is a field that fell. When you let that connection run both directions, from the collider down into the proton and up into the sun, a question starts to press, the one that has been waiting under the whole story. Everything about the Higgs seems set to values that allow a world like ours. The mass that lets atoms hold. The feebleness that lets the sun burn slowly. The tiny difference that makes the neutron heavier than the proton. Each one balanced exactly where it needs to be for matter, for chemistry, for time, for life. Is that balance a coincidence, a necessity, or a sign of something we have not understood about why the universe is built to be lived in? It is hard to look at the list of things the Higgs sets and not feel the pull of a question that physics is not sure how to handle. The strength with which the Higgs grips each particle, the value the field settled into when it fell, the masses that come out of all this, are not obviously the only values that were possible. As far as we can tell from the theory, the field could have fallen into a different value. The dials that set the particle masses could have been turned differently. And almost every other setting we can imagine gives a universe with no chemistry, no stable matter, no slow-burning stars, nothing that could ever wake up inside it and ask why. Consider how narrow the margins are. The Higgs gives the up quark and the down quark slightly different masses, and that small difference makes the neutron heavier than the proton by about 0.1%. That tiny margin is everything. Because the neutron is just barely heavier, a lone neutron decays into a proton, and the early universe ended up with plenty of protons, which are hydrogen, which is the fuel of stars and a key ingredient of water. Reverse the margin, make the proton just slightly heavier than the neutron instead, and lone protons would decay into neutrons. Hydrogen would be unstable. There would be no ordinary hydrogen to speak of, no stable stars of the kind we have, no water. A shift of a fraction of a percent in what the Higgs hands two quarks, and the universe is sterile. Or consider the mass of the electron, which the Higgs sets entirely. It is small, far smaller than the proton, and that smallness is why electrons form large diffuse clouds around nuclei, why atoms are the size they are, why chemistry has the richness it does. Make the electron much heavier, and atoms shrink, bonds change, the whole architecture of molecules shifts. The delicate chemistry that life relies on depends on the electron being light, and the electron is light because its dial on the Higgs field is turned very low, for no reason we can name. Stack these together, and you have a universe that looks, from the inside, suspiciously well arranged for matter to exist. The Higgs values sit in a narrow band that permits atoms, chemistry, stars, and time. Physics has three broad ways of reacting to this, and none of them is comfortable. One reaction is that it is simple coincidence, that the values are what they are, that we should not read meaning into the fact that they allow us, because of course, we find ourselves in a universe that allows us, since we could not find ourselves in one that did not. This is true as far as it goes, but it explains nothing about why a life-permitting universe exists to be found. A second reaction is that there is a deeper theory we have not discovered, one that fixes all these values uniquely, that shows they could not have been otherwise, that the apparent fine-tuning is an illusion that will dissolve once we understand the layer below the standard model. This is the hope that drives much of the search for new physics. The faith that the 24 unexplained numbers will one day be derived rather than measured, that the dials are not free at all but locked by something we have yet to find. A third reaction is the uncomfortable one, the one that sits at the edge of what physics is willing to say. Perhaps there are many universes, or many regions, each with the Higgs field fallen into a different value, each with the dials set differently, the vast majority sterile and empty, and we exist in one of the rare ones where the values happen to allow matter, simply because those are the only ones where anyone can exist to look. In that picture, the fine-tuning is real but unmysterious, because every possible setting is realized somewhere, and observers only arise in the habitable ones. The trouble with this idea is that it may not be testable, and a piece of physics that explains everything and predicts nothing is barely physics at all. Many researchers reach for it only reluctantly, as a last resort, precisely because it can feel like giving up on finding a real reason. I do not think anyone really knows which of these is right, and the not knowing is itself part of what the Higgs revealed. We went looking for the source of mass and found a particle, and in the fine print of that particle's properties, we found a universe balanced on a set of values that we cannot explain, and that happen to be exactly the ones that allow us to ask the question. The Higgs did not create the fine-tuning puzzle. It made it precise. It turned a vague sense that the universe seems arranged for matter into specific numbers, specific dials, specific margins, each one measured, each one unexplained, each one sitting right where it needs to be. There is one family of particles that complicates even this, that does not quite fit the tidy story of the Higgs handing out mass, and they are the most abundant massive particles in the universe, and the Higgs may have little to do with their mass at all. The neutrinos break the pattern, and in breaking it they may point past the Higgs towards something else entirely. Neutrinos are the ghosts of the particle world. They pass through matter, almost without touching it. Right now, trillions of neutrinos from the sun are streaming through your body every second, and almost none of them interact with a single atom of you. They would pass through a wall of solid lead, light years thick, with most of them coming out the other side. They are the most numerous particles with mass in the universe, and they are so faint, so weakly interacting, that for decades physicists assumed they had no mass at all. That assumption turned out to be wrong, and the way it was proven wrong is one of the more beautiful detective stories in physics. Neutrinos come in 3 types, and it was discovered that as they travel, they change from one type into another, oscillating between the 3 kinds as they fly through space. This shape-shifting can only happen if neutrinos have mass, because a truly massless particle, moving at the speed of light, experiences no passage of time and cannot change as it travels. The fact that neutrinos morph in flight is proof that they are not massless, that they carry some tiny weight, enough to let time pass for them, enough to let them change. So neutrinos have mass. Very, very little. Less than a millionth of the mass of the electron, so little we still cannot measure it directly, only prove it is not zero. The neutrinos break the Higgs story right here. The Higgs gives mass to the charged particles, the electron and the quarks, by gripping them through their dials. In principle, it could give neutrinos mass the same way, with a dial of their own. But for the neutrino dial to be turned low enough to produce their absurdly tiny mass, it would have to be set to a value so much smaller than every other dial, so extraordinarily, unnaturally tiny, that most physicists find it hard to believe the neutrino mass comes from the Higgs in the ordinary way at all. The number would be too strange even by the loose standards of the unexplained dials. It would be a dial turned almost, but not quite, all the way off, far below every other particle, with no reason for it to land at such an extreme. So there is a suspicion, a strong one, that neutrinos get their mass by a different mechanism entirely, one that does not run through the ordinary Higgs grip. The leading idea involves a new kind of very heavy partner particle, never seen, whose existence would naturally explain why the neutrinos we observe are so impossibly light. In that picture, the lightness of the neutrino is not an absurdly small dial but a consequence of a seesaw, where the lightness of the neutrino we see is balanced against the enormous heaviness of a partner we have not found. The very faintness of the neutrino would then be evidence for a whole new layer of heavy particles beyond everything in the standard model, beyond the Higgs, at energies far past anything we can currently reach. The Higgs explains the mass of the charged fundamental particles, the electron and the quarks, cleanly and well. It struggles with the neutrinos. And that struggle is one of the clearest signposts that the Higgs is not the final word on mass, that there is at least one kind of mass in the universe it probably does not provide, pointing toward physics that lies past it. The most abundant massive particles in existence may owe their weight to something we have not discovered, and the fact that they exist at all, that they have any mass, is a crack through which we can see that the story is not finished. The neutrinos barely interact, barely register, slip through everything, and yet by the simple fact of having a tiny mass, they may be carrying the biggest clue we have to what lies beyond the Higgs. They are easy to ignore, almost impossible to detect, and they might be the thread that, pulled hard enough, unravels the next layer of physics. The universe hid one of its loudest hints inside its quietest particle. And the neutrinos are not the only place where the Higgs story collides with a number that should not be what it is. There is one more mismatch, larger than all the others, the single worst prediction in the history of physics, and the Higgs sits right in the middle of it. It has to do with the energy of empty space itself, the energy stored in the full vacuum, and what that energy should weigh. When you add up the energy that should be sitting in the vacuum, including the energy of the fallen Higgs field, the answer disagrees with reality by the largest margin any theory has ever been wrong by. The vacuum is full, we have established that, full of fields holding their values, the Higgs among them sitting in its fallen valley. A field sitting in a valley has energy, even at the bottom, even when nothing is happening. The fallen Higgs field carries energy everywhere, throughout all of space, simply by being switched on. And every other field, with its constant quantum flickering, also carries a baseline energy in the vacuum. So empty space, the full vacuum, should have a total energy, an energy per volume that exists everywhere there is space at all. This is not just bookkeeping, because energy gravitates. By Einstein's equation, energy has mass, and mass bends space. So the energy of the vacuum should have a gravitational effect on the universe as a whole. It should push on the expansion of space itself. The energy of empty space is exactly the kind of thing that would speed up or slow down the growth of the universe, and we can measure how the universe is expanding, so we can compare what the vacuum energy should be to what it apparently is. When you calculate how much energy the vacuum should hold, adding up the contributions from the fields, including the fallen Higgs, you get a number that is larger than what we actually observe by a factor with about 120 zeros after it. Not 120 times too big. A factor of 10 followed by 120 zeros too big. It is so far off that it is routinely called the worst prediction in the history of physics, the largest disagreement between theory and observation ever recorded. The theory says the vacuum should be unimaginably dense with energy. So dense, it should have crumpled the universe into nothing or blown it apart instantly. Reality says the vacuum energy is almost exactly zero, fantastically tiny, just barely enough to gently accelerate the expansion of space over billions of years. The Higgs is tangled directly in this. The energy of the fallen Higgs field is one of the contributions to the vacuum energy, and on its own it should be vast, vastly larger than the observed total. For the final answer to come out as small as it does, the Higgs contribution and all the others must cancel against each other to something like 100 decimal places, leaving almost nothing. It is the same kind of impossible cancellation we saw with the Higgs mass, but far more extreme, the most precise, unexplained cancellation in all of science. Enormous quantities, including the energy of the field that fills space, summing to nearly zero for no reason anyone can find. Nobody knows how this works. It is arguably the deepest unsolved problem in physics, deeper than the lightness of the Higgs mass, deeper than dark matter, deeper than the matter-antimatter imbalance. The energy that should be sitting in the vacuum, much of it from the Higgs, should by every calculation be overwhelming, and instead it is almost perfectly absent, and the absence is so precise that it looks engineered, and no engine has been found. We confirmed that the vacuum is full, that the Higgs field fills space with a value, and therefore with energy. And in the same breath we deepened a mystery about why all that energy does not weigh nearly as much as it should. I find this the most humbling place in the whole story, more humbling than the open questions about the Higgs mass, or the dials, or the neutrinos. Because here, the thing we got most triumphantly right, that empty space is full of fields holding energy, runs straight into the thing we have gotten most spectacularly wrong, the amount that energy should weigh. The same discovery that told us the vacuum is a substance also told us we do not understand the substance at all, that its most basic property, its energy, disagrees with our best theory by more than any quantity has ever disagreed with any theory. We learned that the nothing is full, and then we learned that we cannot explain why the fullness is so light. It would be easy to let all of this, the open questions stacked on open questions, leave a sense that the Higgs gave us nothing but new confusion. That is not the right read. Every one of these mysteries was there before, hidden, unphrased. The Higgs is what made them sharp enough to name. Before the discovery, these were vague unease. After it, they are precise, numbered, measurable puzzles, which is the only state from which a puzzle can ever be solved. A sharp mystery is worth more than a blurry comfort. And all of these sharp mysteries, the mass that is too small, the vacuum energy that is too light, the dials with no explanation, the neutrinos that break the pattern, point in the same direction. They point past what we know, toward physics we have not found, and they tell us where to look next. The Higgs was not the end of the search. It was the map's edge, the place where the known territory stops and the arrow points outward into the dark. What lies past that edge, and how we might ever reach it? Every one of the unsolved problems points outward, past the energies we can currently reach, toward a region of physics that our machines cannot yet touch. The natural response is to build a machine that can reach further. But that response runs into a hard wall, and the wall itself tells you why the search may be slowing. To probe smaller distances and higher energies, you have to collide particles harder, and to collide them harder, you have to accelerate them more, and to accelerate them more while bending them around a ring, you need either stronger magnets or a bigger ring. There is no way around this. The energy you can reach is roughly set by the size of the ring times the strength of the magnets, and both of those have practical ceilings. The magnets are already pushed near the limits of what materials can withstand. So, to go meaningfully higher, the main option is to go bigger. And bigger means rings not of 27 kilometers, but of 100 kilometers. Tunnels longer than some mountain ranges, machines so large and so expensive that building them becomes a question for entire continents and generations, not single laboratories. We found the Higgs, and the Higgs pointed at new physics, and the new physics seems to live at energies just out of reach, and reaching it may require the largest and most expensive scientific instruments ever contemplated, with no guarantee of what they will find. The elegant theories that predicted new particles right around the corner have so far been wrong. The partners that supersymmetry promised have not appeared. So the people planning the next machines cannot promise a specific discovery. They can only say that the questions are real, the energies are higher, and the only way to know what is there is to look the same way every previous generation could only know what was there by building the machine and looking. There are other ways forward besides brute energy, and some of them are subtler and more hopeful. Instead of smashing harder, you can measure what you already have more precisely. Every property of the Higgs, every rate at which it decays into each kind of particle, every detail of how it is produced can be measured more and more exactly, and any tiny deviation from the simple prediction would be a signal of hidden physics leaking into the numbers. This is the strategy of precision rather than power. You do not need a bigger hammer if you have a fine enough ruler. A machine designed to make millions of clean Higgs bosons and measure them to exquisite accuracy might find the crack that a higher energy machine would find by force by catching the Higgs behaving a hair differently than the lone simple particle should. There are also ways to look that have nothing to do with colliders at all. The early universe was the highest energy laboratory that will ever exist, and it left faint records. The patterns in the oldest light in the universe, the slight ripples in the distribution of galaxies, the possible traces of the electroweak transition, all of these carry information about physics at energies no machine will ever reach, frozen into the structure of the cosmos. By reading the sky carefully enough, we might learn about the Higgs and what lies beyond it from the imprint the early universe left behind, a record written when the cosmos itself was hot enough to melt the vacuum. The collider and the telescope become two ways of asking the same question, one by recreating the heat in miniature, the other by reading the ashes the original heat left across the sky. So the path past the edge is not one path. It is a slow convergence of many, bigger machines if the world chooses to build them, finer measurements of the Higgs we have, and careful reading of the relics in the sky. None of them is guaranteed. All of them are slow, measured not in years but in decades, in careers, in the patient handing of a problem from one generation to the next. The people who will eventually answer the questions the Higgs raised are, many of them, not yet born. They will inherit the sharp mysteries we have only just learned to name, and they will have tools we have not yet imagined. And some of them will spend their whole lives on a single piece of the answer, the way the people who found the Higgs spent theirs. There is a humility in accepting that. We reached one edge, and from it we can see that there is more, much more, and we cannot reach it yet, and we may not reach it in our lifetimes, and that is simply how this kind of knowledge accrues. Not in single triumphant leaps, but in long, patient approaches, edge after edge, each one revealing a further edge beyond. The Higgs was an edge. It was a real one, hard one, 50 years in the reaching. And standing on it, the main thing you can see is how much country lies past it, still dark, waiting for machines and minds that do not yet exist. But there is one force that none of these machines, however large, is built to explain, one force that the Higgs touches and yet cannot account for, the most familiar force of all, the one holding you to the bed right now. Gravity sits oddly in this whole story, present everywhere and explained least of all, and the Higgs has a strange and incomplete relationship with it. Why does the field that gives mass have almost nothing to say about the force that mass creates? The Higgs gives particles mass. Gravity is the force that mass produces, the pull between any two things that have mass. So you would expect the Higgs and gravity to be intimate, two sides of one idea, the field that makes mass and the force that mass makes, and they are not. They barely speak. Gravity is the one force the Higgs story does not explain, and the gap between them is where our deepest theory simply stops. Recall the two kinds of mass we untangled long ago. One was how hard gravity pulls on you. The other was inertia, how hard it is to change your motion. The Higgs and the strong force together account for inertia, for the resistance, for the energy bound into matter. But the strange and unexplained fact, the one that bothered physicists for 3 centuries and bothers them still, is that the same number that measures your inertia also measures how hard gravity pulls on you. The resistance and the weight are the same number, always, exactly, for every object, and nothing in the Higgs story says why. The Higgs explains where the inertial mass comes from. It says nothing about why that same quantity should also be the thing gravity grabs. Einstein took that mysterious equality and built a whole theory of gravity on it, a theory where gravity is not a force at all but the bending of space and time by energy and mass. In that picture, mass tells space how to curve, and curved space tells matter how to move, and what we feel as the pull of gravity is just matter following the straightest available path through space that mass has bent. It is a magnificent theory, tested to extraordinary precision, and it makes no reference to the Higgs whatsoever. The Higgs gives a particle its mass. Einstein's gravity takes that mass and curves space with it. The two theories meet at the word mass, and otherwise live in separate worlds, written in different mathematics, never fully joined. And they resist being joined. Every other force has been described in the same language, the language of fields and particles and quantum mechanics, the language in which the Higgs lives. Electromagnetism, the weak force, the strong force, all of them fit together in the Standard Model, all of them carried by particles, all of them quantum. Gravity does not fit. Every attempt to write gravity in that same quantum language, to find the particle that carries it the way the photon carries electromagnetism, runs into infinities and contradictions that no one has resolved. The force that mass creates, the force the Higgs's gift of mass should feed directly into, is the one force we cannot make speak the language of the rest of physics. It stands apart, described by Einstein's curved space, refusing to be quantized, refusing to join. So the Higgs sits in a peculiar position. It is the origin of mass for the fundamental particles, and mass is the source of gravity, and yet the Higgs belongs entirely to the quantum world of fields and particles, while gravity belongs to Einstein's separate world of curved space, and the bridge between them has never been built. The field that makes mass and the force that mass makes are described by two theories that have never been reconciled, that may not even be reconcilable in their current forms.